Something happened yesterday that should not have been possible. Not in the way that rare events are improbable, not in the way that magic tricks seem impossible before you learn the mechanism behind them, not in the soft, colloquial sense of the word where people say, "I can't believe that happened," when a sports team wins against overwhelming odds. Something happened in the deepest, most technically precise sense of the word impossible. Something that contradicts the operating instructions of the universe itself. And the strangest part, the part that should disturb you far more than the event itself, is that it has not happened just once. It has been happening, quietly, repeatedly, in laboratories and telescopes and particle accelerators scattered across the face of this planet, in data sets reviewed by thousands of the most rigorous minds alive, in measurements so careful and so repeated that the margin for human error has been reduced to nearly nothing. It keeps happening, and nobody, not one single physicist, not one cosmologist, not one mathematician working at the outermost edge of theoretical science, can tell you why. You are used to reality behaving itself. You have lived your entire life inside a universe that follows rules, and those rules have been so consistent, so perfectly reliable, that you have stopped noticing them the way you have stopped noticing the weight of the air pressing against your skin. When you drop something, it falls. When you push something, it moves in the direction you pushed it. When the sun sets, it rises again the next morning from exactly the direction it always rises from. These are not opinions. These are not cultural agreements or philosophical positions. They are the mechanical laws of a universe that has been running its program faithfully since roughly 13.8 billion years ago. And they have never, not once in all of recorded human history, not once in any experiment ever conducted, not once in any observation ever made, broken down in any way that science could not eventually account for. Until now, because something is no longer adding up, and the implications of that failure reach so far into the foundations of what we call real, that when you follow them to their conclusion, the conclusion itself starts to dissolve. To understand why what is happening right now is so deeply unsettling, you need to first understand what it means for reality to work correctly. Most people, if you ask them to describe how the universe operates, would reach for words like nature or physics, without thinking much about what those words actually mean. But underneath both of those words is a specific, powerful idea. The idea that the universe is governed by consistent, universal, unchanging laws. Not rules that someone made up, not guidelines that can be revised when they become inconvenient, but actual structural properties of reality that hold everywhere, always, without exception. The same law of gravity that causes an apple to fall from a tree in an English garden operates identically in a galaxy 2 billion light years away. The same electromagnetic forces that make your neurons fire and carry the signals through your body right now are the same forces that bind electrons to atoms in the most remote corner of the observable universe. This is the cornerstone of science, the very foundation that makes science possible at all. It is called the universality of physical law, and for centuries, every experiment, every observation, every measurement has confirmed it. The universe, it seemed, was not random. It was not arbitrary. It was structured, lawful, and coherent. That coherence is not just philosophically reassuring, it is the reason civilization exists. The predictability of physical law is what allows engineers to build bridges that do not collapse, what allows chemists to synthesize drugs that heal, what allows spacecraft to travel hundreds of millions of miles through empty space and arrive within seconds of the predicted time at exactly the predicted location. The ability to predict is the ability to survive, to build, to create. And the ability to predict depends entirely on one fundamental assumption, that the rules of the universe do not change, do not waver, do not hide, and do not lie. Every instrument we have ever built, every formula we have ever written, every model we have ever constructed has been built on that assumption, the way a cathedral is built on its foundation, invisible once the walls rise, but bearing the weight of everything above it. What is happening right now is not a crack in one of the walls. It is a tremor in the foundation itself. Let us begin where physics begins, not with the exotic, not with the strange, but with the ordinary. Imagine a single particle, not a molecule, not an atom, but a fundamental particle, a photon, say a single packet of light. You know certain things about this particle with complete certainty. You know it travels at the speed of light because it is light. You know that if you send it toward a barrier with 2 small openings in it, it will pass through one of those openings and continue to whatever is on the other side. That is what physical objects do. They take paths. They go through one place or another. They are here or they are there, never both simultaneously. This is so basic, so self-evidently obvious that stating it feels almost embarrassing. Of course, a thing is either in one place or another. That is what it means to be a thing. And yet, when physicists actually performed this experiment, when they took single photons and fired them at a barrier with two slits, the famous double-slit experiment that has been replicated tens of thousands of times in hundreds of different variations across more than 2 centuries, the photon did not go through one slit or the other. It went through both, at the same time, alone, by itself. A single individual photon, which should by every law of classical logic and physical intuition be in one location at a time, passed through 2 separate locations simultaneously and interfered with itself on the other side, producing a pattern on the detector screen that is only possible if a wave passed through both slits at once. This is not a measurement error. This is not a trick of instrumentation. This is what actually happens. The interference pattern that appears on the detector screen when photons are fired through the double slit is one of the most beautiful and one of the most maddening things in all of science. It looks like the ripple pattern you see when you drop 2 stones into a still pond at the same time, a series of alternating bright and dark bands where waves reinforce each other and cancel each other out. This pattern can only form if 2 waves are interacting. But here's the part that should make something deep inside you go very quiet. Scientists have fired photons at the double-slit apparatus one at a time, with long intervals between each photon, so that there is absolutely no possibility that any 2 photons could interact with each other. They wait until one photon has been detected before firing the next. They do this thousands of times. And when they look at the accumulated pattern of where all those individual photons have landed on the detector, the interference pattern is still there. Each individual photon traveling alone through space, with nothing else around it, has somehow interfered with itself, as if it existed in multiple places simultaneously, as if it took both paths at once, as if the single, solitary, indivisible particle explored every possible path it could have taken and then arrived having been shaped by all of them. This is not a metaphor. This is the measured, empirical, undeniable result. You might be tempted to explain this away. You might tell yourself that the photon is so small, so fundamentally different from the objects you interact with in everyday life, that perhaps the rules are simply different at that scale. Perhaps quantum mechanics is just the name for the strange behavior of things too small to see, and it does not really challenge anything important about the world you actually live in. This is a comfortable thought. It is also precisely the thought that modern physics has spent the last century systematically dismantling, because the strangeness does not stay small. It does not confine itself to the subatomic realm like a polite guest who knows their place. It bleeds upward into larger and larger scales, and every time physicists have designed an experiment to find the boundary where quantum weirdness ends and classical normalcy begins, that boundary has refused to appear. In 2019, scientists in Vienna successfully demonstrated quantum superposition, the state of being in 2 places at once, with molecules containing almost 2,000 atoms. In 2021, experimenters in Oxford showed entanglement effects between objects large enough to be considered macroscopic by some definitions. The boundary keeps retreating, and there are serious credentialed physicists who now believe it retreats all the way, that there is no boundary at all, that the strange quantum reality is the only reality, and the familiar world you see and touch is a kind of persistent illusion generated by the mathematics of probability, collapsing into the appearance of definite objects. But let us not get ahead of ourselves. Let us stay for a moment longer with the experiment and its implications, because there is one more layer to the double-slit story that transforms it from strange to philosophically catastrophic. When scientists added a detector to the experiment, a device placed at or near the slits to measure which path the photon actually took, something astonishing happened. The interference pattern disappeared. The moment the experiment was set up to detect the photon's path, the photon stopped behaving like a wave and started behaving like a particle. It went through one slit or the other. It stopped interfering with itself. The act of measurement, the act of observation, changed the outcome of the experiment. Not because the measuring device was physically disturbing the photon in some mechanical way, not because the detector was bumping into the particle and nudging it off course, but because the information about the path was available, because the universe, or whatever processes govern quantum behavior, somehow knew that the path was being recorded, and in the presence of that knowledge, or that information, or whatever it actually is, the wave-like behavior collapsed. The particle chose a definite path. It became classical. It became normal. It became the kind of thing that obeys the rules you expect things to obey. The only difference between the two outcomes was whether or not anyone or anything was watching. Read that last sentence again. Let it sit with you. The physical behavior of a particle, its actual, literal, measurable trajectory through space, depends on whether or not it is being observed. This is not a statement from mysticism. This is not something from a philosophy seminar on the nature of consciousness. This is the reproducible, peer-reviewed, experimentally verified result of one of the most replicated experiments in the history of science. The implication is staggering, and it has never been fully resolved. It means that at the most fundamental level we have been able to probe, reality does not have definite properties until those properties are measured. Before measurement, a particle does not have a specific location. It has a probability distribution across all the locations it could possibly occupy, a superposition of all possible states, a shimmer of potential rather than a fact of position. And something about the act of measurement, something about the interaction between the quantum system and whatever is doing the measuring, forces that shimmer of potential to collapse into a single, definite fact. Reality, at its deepest level, appears to be made not of things but of possibilities, and those possibilities only become things when something looks at them. This discovery, formally encoded in quantum mechanics, which is the most precisely tested theory in the history of science, accurate to more than 10 decimal places in its predictions, is already enough to keep a thoughtful person awake at night. But it is only the first crack. It is the first small tremor before an earthquake whose full magnitude has not yet been felt. Because quantum mechanics does not stand alone in describing reality, it shares the job with another theory, equally powerful, equally tested, equally confirmed by experiment after experiment after experiment. That theory is general relativity, and it describes not the behavior of particles, but the behavior of space itself, of time, of gravity, of the large-scale structure of the cosmos. And here is the thing that physicists do not always say loudly enough, the thing that should be headline news every single day, but somehow remains the quiet, poorly acknowledged secret at the center of theoretical physics. Quantum mechanics and general relativity are mutually incompatible. They cannot both be correct. They cannot coexist in a single, unified, coherent description of reality. And yet both are correct. Both are verified. Both are the most accurate descriptions of their respective domains that human beings have ever produced. Reality, in other words, is obeying two sets of rules that contradict each other, and no one can figure out how that is possible. To appreciate the depth of this contradiction, you need to understand what general relativity actually says about the nature of space and time. Einstein's great insight, the one that transformed physics in 1915, was that space and time are not a fixed, rigid stage on which the events of the universe play out. They are not a background. They are a fabric, a dynamic, flexible, four-dimensional structure that can bend and stretch and warp in the presence of mass and energy. A massive object like a star does not sit in space and pull things toward it through some mysterious, invisible force, the way Newton imagined. Instead, the mass of the star bends the fabric of space-time around it, creating a curvature, and other objects moving through that curved space-time follow the curvature the way a marble rolls toward the bottom of a bowl. Gravity is not a force. Gravity is geometry. It is the shape of space-time itself. This is a description of reality so alien to intuition that most people cannot quite fully absorb it, and yet every experiment, every observation, every measurement ever made confirms it. The bending of light around massive objects, the precise timing corrections that GPS satellites must make to account for gravitational time dilation, the detection of gravitational waves, ripples in space-time itself, by the LIGO Observatory in 2015. All of it confirms that general relativity is correct, and quantum mechanics is also correct. It correctly describes every interaction between particles at the subatomic level. It successfully predicted the existence of the Higgs boson, confirmed in 2012 at the Large Hadron Collider, with a precision that left no room for doubt. It underpins the design of every semiconductor, every laser, every MRI machine. Without quantum mechanics, the technology of the modern world simply would not function. And yet quantum mechanics operates on an entirely different set of assumptions about reality than general relativity does. Quantum mechanics assumes that space and time are fixed, smooth and unchanging, a background against which quantum events occur. It treats space-time exactly the way Newton did, as an immovable stage. General relativity, meanwhile, says that stage is not fixed at all, that it bends and curves and responds dynamically to matter and energy. These are not minor technical differences that can be smoothed over with a bit of mathematical ingenuity. They are foundational conceptual incompatibilities. They describe reality in ways that logically cannot both be true, and yet both are true, verified daily by instruments and technologies that depend on their accuracy. This is the central crisis of modern physics, and it has been the central crisis for nearly a century. The universe is running on two incompatible operating systems simultaneously, and somehow, impossibly, it works. The failure to unify these two theories is not for lack of trying. Some of the greatest minds of the 20th and 21st centuries have devoted their entire careers to solving this problem. String theory emerged in the 1970s and 1980s as one of the most ambitious attempts, a framework in which the fundamental constituents of reality are not point-like particles, but tiny, one-dimensional vibrating strings of energy whose different modes of vibration correspond to different particles. String theory seemed to offer a path to unification, a way of making quantum mechanics and gravity speak the same mathematical language. It attracted enormous intellectual investment and produced extraordinary mathematical beauty. It also predicted the existence of 6 or 7 additional dimensions of space beyond the 3 we can perceive, curled up at scales so small they cannot currently be detected. And after decades of intense development, string theory has not produced a single unambiguous confirmed experimental prediction. Not one. It remains, in the view of many physicists, an extraordinarily elegant mathematical structure with an uncertain relationship to physical reality. It may be the deepest truth ever discovered by human minds, or it may be the most spectacular intellectual dead end in the history of science. After 50 years, physicists still cannot tell which. Loop quantum gravity is another approach, one that takes the insight of general relativity more seriously and attempts to quantize space-time itself, to treat the fabric of space as made of discrete, indivisible units, granules of geometry at the smallest possible scale, the so-called Planck length, which is approximately 10 or 35 meters, so small that comparing it to a proton is like comparing a proton to the observable universe. Loop quantum gravity predicts that if you could zoom in far enough, impossibly far, far beyond anything any instrument could ever achieve, you would find that space itself is not continuous and smooth but granular, like a photograph that pixelates when magnified too much. This is a radical idea, and it has produced some beautiful mathematics and some testable predictions, but it has also encountered profound difficulties, and it remains far from a complete theory. The problem is not that physicists are not smart enough. The problem runs much deeper than that. The problem is that every time someone constructs a mathematical framework that successfully combines the key features of both quantum mechanics and general relativity, the framework produces infinities, literal mathematical infinities, where there should be finite numbers, infinite energies, infinite densities, values that mean nothing, nonsense outputs from what should be sensible equations. The universe, it appears, does not want to be described in a way that is both quantum and gravitational simultaneously, as if reality itself is resisting the attempt to understand it at its deepest level. And then there is the Hubble tension, and this is where something goes from philosophically troubling to actively empirically alarming. The Hubble constant is a number that describes the rate at which the universe is expanding, how fast galaxies are moving away from each other as space-time itself stretches. It is one of the most fundamental parameters in cosmology, a number that appears in virtually every equation used to describe the large-scale behavior of the universe. You would think that measuring it would be straightforward, at least in principle. You look at how fast distant objects are receding, you factor in the known physics of cosmic expansion, and you arrive at a number. And for a long time, that is essentially what cosmologists did, and they arrived at a number, and they were satisfied. But then two completely different methods of measuring the Hubble constant were developed. Two methods based on entirely different physical phenomena, using entirely different instruments, calibrated by entirely different processes, with independent sources of error and independent teams of scientists checking each other's work. And the two methods gave different answers. Not slightly different, not different within the range of experimental uncertainty, but significantly, stubbornly, reproducibly different. One method, which measures the cosmic microwave background radiation, the ancient afterglow of the Big Bang, gives a Hubble constant of about 67.4 kilometers per second per megaparsec. The other method, which measures the brightnesses of certain types of stars called Cepheid variables and uses them as cosmic distance markers, gives a value of about 73 kilometers per second per megaparsec. That difference, roughly 8%, might sound small in absolute terms, but in cosmological terms it is enormous, and it has refused to go away. Researchers have spent years trying to find the error, They have checked and rechecked every instrument. They have reanalyzed every dataset. They have used entirely new techniques, including the observation of gravitational wave events and the light echoes around distant quasars, and found results that split the difference or complicate the picture further rather than resolving it. As of the most recent publications, the tension remains. The two methods of measuring the expansion rate of the universe give different answers, and neither is wrong. Both measurements are now so precise with uncertainties so small that there is statistically almost no chance both are measuring the same true value, which means one of two things, and neither is comfortable. Either there is a systematic error in one or both methods that has somehow eluded detection by hundreds of independent scientists over decades of checking, or the standard model of cosmology, the model that describes the history and structure of the universe from the first fractions of a second after the Big Bang to the present day, is fundamentally incomplete, missing some ingredient, some phenomenon, some physics that we have not yet discovered. The universe is expanding at a rate that two different measuring tools cannot agree on, and the most likely explanation is that our map of reality has a blank space in it where something crucial should be. That blank space has a companion, and it is perhaps the most humbling admission in the history of human knowledge. When cosmologists add up all the matter and energy they can detect in the universe, all the stars, all the planets, all the gas clouds, all the radiation, everything that interacts with light and is therefore, in principle, visible to some kind of telescope, they find that it accounts for approximately 5% of the total mass energy content of the universe. 5%. The other 95% is invisible. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation in any way that our instruments can detect. It is inferred to exist only because of its gravitational effects on the things we can see, because galaxies rotate in ways that make no sense unless there is vastly more mass there than we can account for, because galaxy clusters bend the light of objects behind them with far more gravitational force than their visible mass could produce, because the large-scale structure of the cosmos, the way galaxies are arranged into filaments and walls, and enormous voids across hundreds of millions of light-years, cannot be reproduced by any simulation that includes only the matter we can see. Something else is there, something vast, something that outweighs everything visible in the universe by a factor of 19 to 1, and we have absolutely no idea what it is. The invisible mass has a name, dark matter. The name was chosen with characteristic scientific sobriety, and it communicates exactly how much we know about it, which is to say, almost nothing. We know it exists because the gravitational ledger does not balance without it. We know it must be some kind of particle, or collection of particles that does not interact with the electromagnetic force, that is transparent to light in the most fundamental sense. We know it must be cold in the cosmological sense, meaning it moves slowly relative to the speed of light, because simulations of galaxy formation only match what we observe if the dark matter is moving slowly. Beyond that, the picture dissolves into speculation. Physicists have proposed dozens of candidate particles, WIMPs, axions, sterile neutrinos, primordial black holes, and increasingly exotic options. And every single one of these candidates has been searched for in dedicated experiments of extraordinary sensitivity, and not one has been found. The Large Underground Xenon Detector in South Dakota, the Panda X experiment in China, the Xenon 1T experiment in Italy's Gran Sasso Mountain, underground laboratories of unbelievable precision, shielded from cosmic rays by kilometers of rock, capable of detecting the tiniest energy depositions in ultra-pure liquid xenon, have all returned the same result. Nothing. Not a single confirmed dark matter particle interaction. Not one. There is a moment in science when the absence of a result becomes itself a profound result. When you have searched long enough, carefully enough, at large enough scales and with sensitive enough instruments, and still found nothing, the most alarming possibility is not that your instruments are not good enough, but that the thing you are looking for is not where you expected it to be, or is not the thing you expected it to be at all. Some physicists are now seriously entertaining the idea that dark matter does not consist of particles at all, that it might instead be a modification to the laws of gravity that we have not yet understood. Modified Newtonian dynamics, or MUND, and its relativistic extension, tensor vector scalar gravity, attempt to explain galaxy rotation curves without invoking any new particle by subtly altering the way gravity behaves at very low accelerations. These alternatives have had some notable successes in explaining certain galactic observations, but they struggle with others, particularly the behavior of galaxy clusters. where particle-based dark matter models work much better. Neither model is complete. Neither model explains everything. And the fact that we are caught between two incomplete explanations for 95% of the universe is not a footnote. It is a confession. We do not know what most of the universe is made of. Of the remaining 27% that is not dark matter, the vast majority, roughly 68% of the total mass energy of the universe, is something even more mysterious, something that physicists have named with equal epistemic humility: dark energy. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. This is the discovery that won the 2011 Nobel Prize in Physics. In 1998, two independent teams of astronomers measuring the distances and recession velocities of Type Ia supernovae, stellar explosions so bright they can be seen across billions of light years, found that the universe is not just expanding, but expanding faster and faster as time passes. The expansion is accelerating. This was so unexpected, so contrary to everything that theory had predicted, that the initial reaction of many physicists was to assume there was an error in the data. There was no error. Every subsequent observation has confirmed it. The universe is getting bigger at an increasing rate, as if some invisible energy embedded in the fabric of space itself is pushing everything apart with ever-increasing force. In Einstein's equations, this shows up as a cosmological constant, a term that Einstein himself introduced and then famously discarded, calling it his greatest blunder. History repaid that self-criticism with irony by proving the constant was necessary after all. But here is the problem. Quantum field theory, the extension of quantum mechanics that describes the behavior of fields and the particles that are their excitations, predicts that empty space should have an energy. Vacuum energy, it is called. The vacuum of space is not nothing. According to quantum mechanics, it is a seething foam of virtual particles constantly popping in and out of existence, and all of those virtual fluctuations should contribute an energy density to space itself. When physicists calculate what this vacuum energy should be, when they do the math with quantum field theory, they get a number, and when they compare that number to the observed value of the cosmological constant, the value inferred from the accelerating expansion of the universe, the comparison produces one of the most embarrassing discrepancies in the history of science. The predicted value is larger than the observed value by a factor of roughly 10 to the power of 120. That is a 1 followed by 120 zeros. This is not a small error. It is not an error that can be explained by some overlooked systematic effect or some subtle mistake in the calculation. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of physics. The universe is using an amount of vacuum energy that is incomprehensibly, inexplicably, almost satirically smaller than what quantum mechanics says it should be, and no one can explain why. This discrepancy has a name: the cosmological constant problem, and it has been called the worst theoretical prediction in the history of physics. Think about what that means. The most successful theory of the microscopic world, quantum field theory, when applied to the question of the energy of empty space, gives an answer that is off by 120 orders of magnitude. If your calculation of how far you need to drive to reach a destination was off by that factor, and you were trying to get to a store that is 1 mile away, your calculation would tell you to drive a distance greater than the observable universe. The error is so catastrophic, so complete, that many physicists believe there must be some deep cancellation mechanism at work, some unknown process that takes the enormous predicted vacuum energy and cancels almost all of it out, leaving the tiny observed residue. But no one knows what this mechanism is. No one has found it. And the fact that the cancellation, if it exists, would need to be accurate to 120 decimal places, that it would need to be tuned with a precision that defies any natural explanation, suggests to some physicists that the cosmos is not the product of blind physical law at all, but of some principle of selection that we do not yet understand, possibly involving an enormous number of different universes, each with different values of the cosmological constant, with our universe being one of the rare ones where the value is small enough for structure to form and observers to exist. This is the anthropic argument, and its invocation by serious physicists is itself a sign of how deep the crisis runs. When the best answer to a question is, we live in a universe where this happens to be true because in universes where it is not true, there is no one to ask the question. You are standing at the edge of what physics can currently explain. Let us return to something more immediate, more close-up, more intimate, let us return to the act of measurement itself and look at what happens when you take the principles of quantum mechanics to their logical conclusion. You already know that the act of observation collapses the quantum wave function, that measuring a particle's position forces it to occupy one definite location rather than a superposition of many. But what exactly does the measuring device have to be? What counts as an observation? Does it have to be a conscious mind? Does it have to be a physical detector? Does it have to involve any kind of information processing at all? These questions are not merely philosophical, they are technical, and the answers to them determine what quantum mechanics actually says about the nature of reality. Different interpretations of quantum mechanics give wildly different answers, and the astonishing thing is that they are all, by construction, consistent with every experiment ever performed. They all predict the same experimental outcomes. They differ only in what they say reality actually is in between measurements, and in what they say about the nature of the observer, which means that the experimental data cannot tell us which interpretation is correct, which means we know how to predict what reality will do, but we do not know what reality is. The most famous interpretation, the one you encounter first in any physics education, is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. Copenhagen says essentially, do not ask what the particle is doing before it is measured. The question is meaningless. Only measurement results are real. Between measurements, talking about the state of a particle is like talking about the sound of a tree falling when no one is there to hear it. The question has no physical content. This is a pragmatic, operational stance, and it has served physics extraordinarily well as a working framework for nearly a century, but it is deeply unsatisfying as a description of reality, because it seems to say that reality itself, the particle, the electron, the atom, does not exist in any definite sense until someone looks at it. It puts the observer at the center of the universe, which is either profound or incoherent, and it is genuinely difficult to tell which. Many working physicists adopt Copenhagen without much discomfort, using it as a tool and declining to worry about its metaphysical implications. But the implications do not go away just because you decline to worry about them. They accumulate quietly in the foundations. Hugh Everett III proposed an alternative in 1957 that takes quantum mechanics completely at face value, refusing to invoke any special role for measurement or observation. His idea, now called the many worlds interpretation, holds that the wave function never collapses. Every time a quantum measurement occurs, every time a quantum event with multiple possible outcomes takes place, the universe simply branches. All of the possible outcomes occur. In one branch, the particle goes through the left slit. In another branch, simultaneously the particle goes through the right slit. In one branch, the radioactive atom decays. In another, it does not. In one branch, the cat in the famous Schrödinger thought experiment is alive. In another, it is dead. The universe is constantly unstoppably splitting into an astronomical, perhaps literally infinite, number of parallel branches, one for each possible quantum outcome, and each branch is as real as every other. You, reading this, exist in one branch of an unimaginably vast multiverse. Every decision you have ever made, every random quantum event in your brain or in the cosmos around you, has generated an entire new universe, diverging from yours at the moment of branching, never to interact with yours again. The many worlds interpretation makes the same predictions as Copenhagen for every experiment. It requires no special role for observers. It is, in some sense, the most mathematically natural extension of quantum mechanics, and it implies that you are just one version of you, living in one of infinitely many universes, most of which you will never be able to detect, communicate with, or know about in any way. There are other interpretations, Bohmian mechanics, which says particles always have definite positions but are guided by a real, physical quantum wave that is never observed directly. Relational quantum mechanics, which says quantum states are always relative to a particular observer, and there is no absolute observer-independent reality at all. Cubism, which treats the quantum wave function not as a physical object, but as a representation of an agent's beliefs about the outcomes of their future experiments, making quantum mechanics not a theory of reality, but a theory of how rational agents should update their knowledge. All of these interpretations, every single one, is consistent with every experiment ever performed. None of them can be ruled out by any measurement currently possible. This means that the most successful scientific theory ever devised the theory that underpins all of modern physics and chemistry and has been confirmed to a precision that no other theory in history has achieved, has at its core a question it cannot answer. What is real? What actually exists? And the answer depends not on any experiment, but on which philosophical framework you choose to adopt. Science, which is supposed to be the method for finding out what is real, has built its most successful theory on an irreducible philosophical ambiguity about the nature of reality itself. If that were the end of the strangeness, it would already be enough to permanently alter the way you see the world. But it is nowhere near the end, because now we need to talk about entanglement, about what Einstein called spooky action at a distance, and considered so absurd that he used it as evidence that quantum mechanics must be incomplete. Quantum entanglement is a phenomenon in which two particles interact in such a way that their quantum states become correlated, and this correlation persists even when the particles are separated by arbitrarily large distances. Take two photons and produce them in a way that entangles their polarizations, a property related to the orientation of their electric fields. The two photons fly apart in opposite directions. You and a friend each take one, and your friend travels to the other side of the planet, or to the other side of the solar system, or hypothetically to the other side of the galaxy. You measure the polarization of your photon and find that it is, say, vertical, instantaneously, not after any delay, not after a signal has had time to travel. Your friend's photon acquires the complementary polarization, not because a message was sent, not because the photons were carrying hidden information about their polarizations all along, but because they are entangled and the measurement of one instantaneously determines the state of the other, regardless of the distance between them. Einstein rejected this picture. He insisted in a famous 1935 paper written with Boris Podolsky and Nathan Rosen, the EPR paper, that quantum mechanics must be incomplete, that the particles must actually carry hidden variables, encoding their polarizations from the moment of their creation, and that the appearance of instantaneous correlation was just a consequence of not knowing those hidden variables. It was an eminently reasonable position. It preserved the idea that no information or influence can travel faster than light, which is a cornerstone of relativity. It preserved the idea that particles have definite properties whether or not anyone is measuring them. It was, in every intuitive and philosophical sense, the sane explanation, and it was proven wrong in 1964, when physicist John Bell derived a mathematical inequality, now known as Bell's theorem, that could distinguish between quantum mechanics and any hidden variable theory, no matter how cleverly designed. Bell showed that if particles carry hidden variables that determine their measurement outcomes in advance, the correlations between measurements of entangled particles must obey certain statistical limits. He calculated what those limits are, and then experiments were done, the first by John Clauser in 1972, refined by Alain Aspect in 1982, and perfected with steadily increasing precision and increasingly closed loopholes over the following decades, culminating in experiments so airtight that the 2022 Nobel Prize in Physics was awarded to Aspect, Clauser, and Anton Zeilinger specifically for this work. The results were unambiguous. The correlations between entangled particles violate Bell's inequalities. They are stronger than any hidden variable theory allows. The particles are not carrying secret instructions. They do not have predetermined answers to the questions that measurements will ask them. And yet, when you measure one, the other instantly knows, or behaves as if it knows, what answer to give. Something is connecting them across space in a way that has no mechanism, no signal, no carrier, no delay. Einstein's intuition was wrong. Spooky action at a distance is real. What does this mean? What does it actually concretely mean that two particles separated by any distance can be instantaneously correlated in a way that cannot be explained by any local hidden mechanism? It means that the universe is, at its most fundamental level, non-local. It means that the assumption of locality, the assumption that what happens at one location in space can only be influenced by things in its immediate vicinity, that influences propagate through space at finite speeds, that distant regions of the universe are genuinely causally separate, is false, not approximately false, not false in some exotic limiting case. Fundamentally, structurally, irreducibly false. The universe is not made of separate things in separate places. It is something more like a single, unified, deeply interconnected system in which separate and distant are, at the deepest level, illusions. The separateness you see, the fact that you are here and something else is there and the two of you are genuinely distinct, is a property of the classical macroscopic world that emerges somehow from a quantum reality in which that separateness does not fully apply. and no one can explain how. No one can point to the mechanism by which a non-local quantum reality gives rise to a local classical appearance. It just does, and the mathematics describes it perfectly, and the physical picture remains, after nearly a century, completely obscure. There is a way in which the non-locality of quantum mechanics intersects with the structure of space-time from general relativity to produce a problem so deep it is almost meditative to contemplate. General relativity tells you that nothing, no object, no signal, no influence, can travel faster than light. This is not just a speed limit. It is a structural feature of space-time that preserves causality, the principle that causes precede their effects, that the past influences the future and not vice versa. If something could travel faster than light, it could, in certain reference frames, travel backward in time, arriving before it was sent. This would create causal paradoxes. The grandfather paradox, where you travel back in time and prevent your own existence, or more subtle versions involving information that causes itself to be sent, and causality would collapse. The universe would stop making logical sense. So relativity's prohibition on superluminal travel is not a matter of engineering limitations. It is a logical necessity for a coherent reality. And yet entanglement produces correlations that are instantaneous, that cannot be explained by any signal traveling at any speed, including the speed of light. The two things, the locality that relativity requires and the non-locality that quantum mechanics demonstrates, should be incompatible. And in a certain technical sense, they are reconciled by the fact that entanglement cannot be used to transmit usable information faster than light. You cannot control which outcome you get when you measure your particle, so you cannot encode a message in the correlations. But the deeper tension remains. The universe appears to be both local, at the level of information transfer, and non-local, at the level of physical correlation. And the reason those two things can coexist is not understood. Not really. Not in any way that produces a satisfying physical picture. Now think about what time is. You have lived every moment of your existence moving forward through time, from past to future, from cause to effect. Time, in your experience, has a direction. Memory reaches backward. Anticipation reaches forward. The past is fixed, and the future is open. This directional quality of time is so fundamental to experience that it seems as if it must be written into the laws of physics themselves, as if the arrow of time must be as basic as anything in the universe. And yet, with a single striking exception, the fundamental laws of physics are time-symmetric. The equations of quantum mechanics, of electromagnetism, of general relativity, run them forward, and they correctly describe how a physical system evolves. Run them backward. Replace every instance of time with negative time, and they still correctly describe a physically possible evolution. The laws do not care which direction time runs. A video of two billiard balls colliding looks physically identical whether played forward or backward. A video of a shattered glass spontaneously reassembling itself from fragments on the floor and leaping back onto the table, however, looks immediately, obviously, unmistakably wrong. And yet that process is not forbidden by any fundamental law. It is merely extraordinarily improbable. The arrow of time, the reason the future is different from the past, the reason entropy increases, the reason broken glasses do not reassemble themselves, is not a fundamental law of nature. It is a statistical consequence of initial conditions. It comes from the fact that the early universe happened to be in a state of extraordinarily low entropy, and no one knows why. The mystery of time's arrow is not just cosmological, it is personal, in the most intimate sense. Your memories are records of the past, not of the future, because your brain is a physical system embedded in a universe with an arrow of time, a universe in which entropy increases toward the future. Your sense of moving through time, of experiencing a present moment that separates a fixed past from an open future, is a product of thermodynamics. It is a product of the fact that the universe started in a very special, very low entropy state. If the universe had started in a state of maximum entropy, in a state of complete disorder, there would be no arrow of time. There would be no past or future, no cause or effect, no memory, no anticipation, no narrative of experience. In the most literal sense, the fact that you experience time as flowing from past to future is not a law of physics. It is a coincidence of initial conditions. And the question of why those initial conditions were what they were, why the Big Bang produced a universe of extraordinarily low entropy rather than one of high entropy, is one of the deepest unsolved problems in physics. The physicist Roger Penrose has estimated that the probability of the universe beginning in a state of low enough entropy to produce the arrow of time we observe is 1 in 10 to the power of 10 to the power of 123, a number so incomprehensibly small that writing it out would require more digits than there are particles in the observable universe. And yet here we are. Perhaps even more disturbing than the mystery of time's arrow is what happens when you look at time not as a flow, but as a dimension. In Einstein's relativity, time is not separate from space. It is unified with space into a four-dimensional structure called space-time. And in this framework, past, present, and future all exist simultaneously. They are not different things. They are different locations in a four-dimensional manifold, the way north and south are different locations on a two-dimensional map. The physicist's view of space-time is what philosophers call the block universe, a picture in which the entire history of the universe, from the Big Bang to whatever ending it may eventually have, exists as a single, static, four-dimensional block. In this picture, now is not a special, privileged moment. It is just the moment you happen to be located at. The way here is just the location you happen to be at on a map. The past still exists. The future already exists. Your future self is already there, at a different location in the block, and there is a real sense in which it is equally real to the present you. Nothing is happening in the block universe. Everything just is. The flow of time, the sense of moments passing, the feeling of the present marching relentlessly forward, all of that is not a feature of the universe. It is a feature of your experience. And why you experience a static four-dimensional block as a dynamic, flowing sequence of moments is one of the most baffling unsolved problems at the intersection of physics and neuroscience and philosophy. Nobody knows. And this is the place where the most unsettling possibility begins to crystallize. The possibility that what you experience as reality may not be what reality actually is. Not because your senses are unreliable, not because your instruments are imprecise, but because the very structure of human perception and human cognition may be fundamentally mismatched with the actual structure of the universe. Your brain evolved over millions of years to navigate a medium-sized world at medium speeds with medium levels of energy. It is a prediction machine, constantly building a model of the environment and using that model to guide behavior. The world it models is the classical macroscopic world of everyday experience, a world of solid objects, continuous motion, definite positions, flowing time, and clear causal relationships. That model is extraordinarily good at what it evolved to do. But the universe is not medium-sized or medium speed. At the very small, it is quantum. At the very large, it is relativistic. At the very energetic, it is something we have barely begun to describe. And between what your brain naturally models and what the universe actually is, there may be a gap so fundamental that your direct experience of reality is not just incomplete, but structurally misleading, like trying to understand the behavior of a fluid by looking only at a solid frozen cross-section of it. You are not seeing the universe. You are seeing what the universe looks like through the narrow, medium-scale filter of human nervous systems. And the question of what the universe looks like without that filter, what it actually is in itself, independent of any observer, may not be answerable from inside the filter. The philosopher Thomas Nagel once asked what it is like to be a bat, whether the echolocation experience of a bat, the way it perceives the world as a three-dimensional map of sound reflections, is something a human mind can ever truly access. His answer was no. The bat's experience of the world is so structured by a sensory modality so different from our own that no amount of description or analogy can fully convey it to a being who has never experienced it. Now ask the same question about a quantum particle, or about space-time itself, or about whatever it is that underlies both quantum mechanics and general relativity in some deeper, unified theory. What is it like to exist at the Planck scale, where space and time themselves may become discrete and foamy? What does the block universe feel like from the inside? What is the experience of a superposition? These questions may be as meaningless as asking what red looks like to a being with no vision. And if they are, then the gap between what the universe is and what any observer can know about it may be unbridgeable, not because we are not clever enough, but because knowing requires a knower, and every kind of knower brings its own limitations, its own distortions, its own filters that shape the known. Let us talk about black holes, because black holes are where the crisis between quantum mechanics and general relativity becomes not a theoretical problem, but a physical catastrophe. A black hole forms when a sufficiently massive object collapses under its own gravity to a point where the curvature of space-time becomes so extreme that not even light can escape. The boundary of no return is called the event horizon, and beyond it, according to general relativity, all paths through space-time lead inward, toward the singularity at the center, where the curvature of space-time becomes literally infinite, and the equations of general relativity simply break down. They produce meaningless outputs, which is the mathematical way of saying that physics as we know it stops working. The singularity is a place where reality, in the sense of physical laws, ceases to exist, and general relativity predicts it confidently and completely without apology. This is already remarkable, a theory of the physical world predicting its own failure, a description of a region where description is no longer possible. But it gets worse. In the early 1970s, Stephen Hawking combined quantum mechanics with general relativity in a semi-classical approximation, not a fully quantum theory of gravity, but a hybrid that treats the gravitational field of the black hole classically, while treating the quantum fields around it quantum mechanically. And from this hybrid treatment, Hawking derived one of the most surprising and most consequential results in modern physics. Black holes radiate. They are not perfectly black. Due to quantum effects near the event horizon, they emit a faint thermal radiation, now called Hawking radiation, and over time, this radiation carries away energy, causing the black hole to slowly evaporate and eventually disappear. This is a beautiful result. It connects thermodynamics, quantum mechanics, and gravity in a deep and surprising way. But it carries within it a paradox that has tortured theoretical physics for 50 years, and that paradox is called the black hole information paradox. Here is the problem. According to quantum mechanics, information can never be destroyed. This is not a technological limitation, it is a fundamental law. The quantum mechanical evolution of a system is always, in principle, reversible. If you know the final state of a quantum system, you can calculate its initial state. Information in quantum mechanics is perfectly conserved, but if a black hole evaporates by emitting Hawking radiation, radiation that is purely thermal, purely random, containing no information about what fell into the black hole, then the information about everything that ever fell in is destroyed when the black hole finally evaporates. A star, a spaceship, a library of books, a human body, anything that fell into the black hole and passed the event horizon is reduced to its mass and charge and angular momentum, and when the black hole evaporates, that precise, specific quantum mechanical information about the exact state of every particle that fell in is gone. Permanently gone, which quantum mechanics says is impossible, which relativity says is inevitable. This is not a paradox you can resolve with ingenuity. It is a direct head-on collision between two fundamental laws of physics. The attempts to resolve the information paradox have generated some of the most creative and extreme proposals in the history of theoretical physics. Some physicists argue that the information is encoded in subtle correlations in the Hawking radiation, that the radiation is not quite thermal, that it carries information in a form so delicate and scrambled that it is effectively invisible, but theoretically recoverable. This is the position of most modern string theorists, following a calculation by Juan Maldacena in 1997 that suggested a deep equivalence between a gravitational theory in a region of space and a quantum field theory on the boundary of that region, an equivalence known as the AD-CFT correspondence, but demonstrating that the radiation actually encodes the information in a specific, verifiable way remains enormously difficult. Others have argued for a much more radical resolution, the firewall proposal of Almheri, Marolf, Polchinski, and Sully, which suggests that the event horizon is not a smooth, invisible surface that infalling observers cross unaware, as general relativity predicts, but a wall of high-energy radiation that incinerates anything that reaches it, preserving quantum information, but violating the predictions of general relativity. A third option, proposed by various physicists including Penrose, is that quantum mechanics itself needs modification, that the evolution of quantum states is not always reversible, that information genuinely can be destroyed, and that a new theory is needed that allows for non-unitary evolution in certain extreme circumstances. Each of these proposals requires abandoning something we thought was certain. Each requires that something we have tested and confirmed and built technology upon is, in some regime, wrong. The implications of the black hole information paradox extend far beyond black holes themselves. If information can be lost in a black hole, then the universe is not reversible, and the past cannot be reconstructed from the future. The universe has a direction, a one-way quality, even in its most fundamental quantum laws that we did not previously know about. If information cannot be lost, if the resolution is that Hawking radiation somehow encodes everything that fell in, then the nature of the event horizon is not what general relativity describes, and the principle of equivalence, the cornerstone of general relativity that says freely falling observers cannot distinguish their situation from flat spacetime, is violated. Either way, something we believed with high confidence is wrong. And the question of which wrong thing to sacrifice, which cornerstone to remove, has divided the physics community for decades and continues to do so today. The crisis is not rhetorical, it is structural. What physicists often speak about quietly, in seminars and conference hallways and the careful language of papers where extraordinary claims must survive peer review, is the growing sense that all of these problems, the Hubble tension, the cosmological constant problem, the dark matter mystery, the quantum gravity incompatibility, the information paradox, the measurement problem, may not be separate issues with separate solutions, but different facets of a single, deeper problem. That there is something wrong with our picture of reality at a more fundamental level than any of these individual puzzles suggests on its own. The great physicist John Archibald Wheeler, who coined the term black hole and spent decades thinking about the foundations of physics, developed in his later years a radical idea that he called it from bit, the idea that the universe is, at its deepest level, not made of matter or energy or fields, but of information, that every particle, every physical quantity, every property of every object in the universe arises from the answers to binary questions, yes or no, 0 or 1, and that information is more fundamental than the physical stuff we normally think of as real. Wheeler's vision was that reality is participatory, that the universe cannot exist without observers to ask questions of it, that in asking questions we participate in the creation of reality, rather than merely discovering a reality that was there independently. This is not mysticism. This is one of the most serious and consistently motivated ideas in the foundations of physics, taken seriously by physicists, including David Deutsch, Anton Zeilinger, and a growing number of younger researchers who work on quantum information theory. The idea that information might be the fundamental substrate of reality receives support from an unexpected direction: thermodynamics and entropy. Claude Shannon, working in the 1940s on the mathematics of communication, discovered that the entropy of a thermodynamic system, the measure of its disorder, the quantity that increases with time in the second law of thermodynamics, is mathematically identical to the information entropy of a probability distribution. This is not a coincidence or a metaphor. It is a precise mathematical equivalence. The entropy of a gas and the information content of a message can be computed by the same formula. This connection, developed further by physicists like Rolf Landauer, who showed that erasing a bit of information has a minimum thermodynamic cost, suggests that information and physical reality are not just analogous but genuinely, deeply connected. And if they are, then the fact that the second law of thermodynamics always increases entropy, that disorder always grows, is the same as saying that information is always becoming less accessible, always being scrambled into forms more difficult to recover. The arrow of time is an arrow of information loss, and the universe as a physical system is in some sense a computer, a process of information transformation whose deep nature may be computational before it is material. Eric Verlinde, a physicist at the University of Amsterdam, has proposed that gravity itself is not a fundamental force at all, but an emergent phenomenon arising from the thermodynamics of quantum information. In his framework, called entropic gravity, the gravitational attraction between masses is a consequence of the tendency of information-containing systems to move toward configurations of higher entropy, an emergent statistical effect, like pressure in a gas rather than a fundamental interaction. This would mean that Newton's law of gravity, Einstein's general relativity, and possibly even space-time itself are not basic features of the universe, but effective descriptions that emerge from some deeper quantum information structure. Verlinde's ideas are controversial and not universally accepted, but they are taken seriously by many physicists, and they illustrate the growing conviction that the next major revolution in physics will not come from finding new particles or new forces, but from understanding what space-time and matter and gravity actually are when you look at them at their deepest level. from finding the underlying information structure from which the familiar physics we know emerges, the way temperature and pressure emerge from the statistical behavior of billions of molecules. The emergence of space-time from something more fundamental is not just a speculation, it is increasingly a research program. Physicists working on quantum information theory and quantum gravity have discovered deep connections between the entanglement structure of quantum systems and the geometry of space-time. In the framework of the AD-CFT correspondence, the entanglement between regions of a quantum system on the boundary of a space is related to the geometry of the space-time in its interior. More specifically, the area of surfaces in the interior of the space-time, the amount of space-time volume they enclose, is related to the amount of quantum entanglement between different parts of the boundary theory. This is the Ryuta-Kayanagi formula, and it suggests something extraordinary, that the geometry of space-time, its shape, its curvature, its structure, is encoded in, and perhaps generated by, the entanglement between quantum systems. That spacetime itself is not primary, but is instead a kind of holographic projection arising from quantum entanglement. The three-dimensional space you move through, the geometry that defines the shape of the universe, may be woven out of quantum correlations between systems that exist, in some deeper sense, in a lower dimensional description. Space may not be what it appears to be. It may not be a fundamental feature of reality at all. It may be something that emerges, the way temperature emerges from molecular motion, from a structure in which space does not appear. The holographic principle, the idea that the information content of a three-dimensional region of space can be encoded on a two-dimensional surface surrounding that region, is one of the strangest and most potentially transformative ideas in modern physics. It was first suggested by Gerard 't Hooft and Leonard Susskind in the 1990s, inspired by Hawking's calculation that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is deeply counterintuitive. You would expect the information content of a region of space to scale with its volume. The bigger the room, the more you can pack into it. But the entropy of a black hole, which represents the maximum information that can be stored in any given region of space, scales with the surface area. The universe, or at least any bounded region of it, appears to behave like a hologram, with all the information needed to describe its three-dimensional contents encoded on a two-dimensional boundary. If this is right, and the evidence from string theory and quantum gravity strongly suggests it is, at least in certain theoretical settings, then the three-dimensional world you experience is, in some technical sense, a projection, a holographic rendering of a two-dimensional informational reality. Your depth perception, the distance between here and there, the very concept of space as a three-dimensional container, all of it may be emergent, secondary, a consequence of something that at a more fundamental level has no depth at all. The simulation hypothesis, popular in technological and philosophical circles, takes this idea and runs with it in a direction that is intellectually uncomfortable, but not, strictly speaking, impossible. If the universe is at its base level computational, if it is a process of information transformation rather than a substance, then the question of whether that computational process is running on some physical substrate or on some other kind of substrate becomes genuinely ambiguous. Nick Bostrom's simulation argument, published in 2003, points out that if it is possible to create simulated universes, if consciousness can exist in a simulated environment, then the number of simulated universes that sufficiently advanced civilizations could potentially create is astronomically large, vastly outnumbering the number of non-simulated original universes, in which case, by sheer probability, any given observer is far more likely to be in a simulated universe than in a base reality. This argument is not a proof. It is a probabilistic claim that depends on premises, that simulated consciousness is possible, that advanced civilizations would create many simulations that are not established, but it is also not obviously wrong. And what makes it particularly interesting, from the perspective of the anomalies we have been discussing, is that a simulated universe might display exactly the kinds of features that ours displays: discreteness at the smallest scales, as loop quantum gravity predicts, a finite information density, as the holographic principle implies, an apparent randomness in quantum measurement outcomes, consistent with a random number generator in the simulation's code, and possibly, as some physicists have suggested, artifacts, deviations from perfect simulation, errors in the rendering, places where the rules of the simulation show seams. Whether the anomalies we observe, the Hubble tension, the cosmological constant, the measurement problem, are such seams is a question that cannot currently be answered. But the question itself, once asked, does not quietly go away. More scientifically grounded but equally unsettling is the question of what happens at the Planck scale, the scale at which quantum gravitational effects should become significant, at lengths around 10 to 35 meters and energies around 1019 giga-electron volts. This scale is so far beyond the reach of any conceivable particle accelerator that direct experimental evidence about what happens there may never be obtainable. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 14 tera-electron volts. The Planck scale is a trillion times more energetic than that. And yet, this is the scale at which the assumptions of both quantum mechanics and general relativity should break down, where space-time can no longer be treated as smooth and continuous, where the quantum foam of virtual particles and fluctuating geometry should produce effects that neither theory can describe correctly. Whatever physics operates at the Planck scale is the physics that underlies everything else, the ultimate foundation beneath quantum mechanics and general relativity alike. And it is, for all practical purposes, experimentally inaccessible. We are trying to understand the foundation of reality while standing so far from it that we cannot even see it. Everything we know comes from scales thousands of orders of magnitude above the Planck scale, and we are extrapolating downward, hoping that our equations remain valid in regimes where nothing guarantees they should. The inaccessibility of the Planck scale is a fundamental epistemic barrier, and it raises the question of whether the deepest physical reality is, in principle, knowable at all. This is not a question that physics has traditionally had to face. The history of physics is a history of successively deeper access to the structure of matter, from rocks and water to molecules to atoms to protons and neutrons to quarks and gluons, with each layer revealing new and richer structure below the previous one. The Planck scale may be where this onion finally ends, where there is no smaller layer, where the very concepts of smaller and larger lose meaning because space itself is quantized. Or it may be where our ability to access the next layer ends even if the next layer exists. And if it is the latter, if there are layers of reality beneath the Planck scale that influence what happens at all larger scales, but that cannot, even in principle, be probed by any physical experiment, then physics faces a hard limit not of progress, but of knowledge. The universe may contain truths about its own nature that its own laws prevent from ever being discovered by any observer within it. There is a version of this epistemic limit that is even more immediate and more personal. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is a sphere about 93 billion light-years in diameter. Beyond that horizon, space continues. The universe extends almost certainly far beyond what we can see. How far? We do not know. Cosmological inflation, the theory that the universe underwent a period of extraordinarily rapid expansion in the first tiny fractions of a second after the Big Bang, predicts that the actual universe is vastly, perhaps infinitely larger than the observable portion. If inflation happened, and there is strong evidence that something like inflation occurred, in the form of the extraordinary uniformity of the cosmic microwave background across regions of the sky that should never have been in causal contact, then there are regions of space beyond our horizon that we can never see, never probe, never receive information from. They are forever outside our observational reach, not because our technology is limited, but because the universe is expanding faster than light can cross the distance between us and them. What is in those regions? Are the laws of physics the same there? Are there other arrangements of matter and energy, other cosmological constants, other physical parameters? We cannot know. By the construction of the universe itself, that information is hidden from us. Reality extends beyond our ability to observe it, and the part we cannot observe may be the majority of it. The multiverse, in this context, is not just a speculative idea from science fiction. It is the natural prediction of the most successful theories of early universe cosmology. Inflationary cosmology, in almost all of its variants, predicts that inflation does not end everywhere at once. In most of the universe, inflation continues indefinitely, producing an eternally expanding space in which isolated bubbles, each one a universe like ours, with the inflation ending inside that bubble and matter and radiation forming, nucleate randomly, and evolve according to whatever physical laws happen to apply within that bubble. This is called eternal inflation, and it produces not one universe but an uncountable, perhaps literally infinite, number of bubble universes, each causally disconnected from the others, each potentially with different physical laws, different constants of nature, different amounts of dark energy, different numbers of spatial dimensions, The multiverse of eternal inflation is the natural answer to questions like, why is the cosmological constant the value it is? The answer being that it takes many different values in different bubble universes, and we observe the value we do because we can only exist in a bubble where the value permits the formation of galaxies and stars and planets and observers. This is the anthropic principle, applied at cosmological scales. Many physicists find the anthropic principle deeply unsatisfying, even repugnant. It feels like giving up, like saying, the laws of physics are what they are, because that is what they had to be for us to exist to observe them, which explains everything and predicts nothing. A theory that predicts every possible universe equally is not really a theory at all. It cannot be used to make predictions that can be tested and potentially falsified. It makes physics not a discipline of discovery, but a discipline of explaining whatever is observed by invoking the vast parameter space of the multiverse. Some physicists, like David Gross, have argued passionately that invoking the anthropic principle is a surrender, an abandonment of the scientific goal of finding a unique, principled explanation for the laws of nature. Others, like Steven Weinberg, who made a famous anthropic prediction of the cosmological constant before it was observed, argue that it is the honest acknowledgement of a feature of reality that we did not choose and cannot escape. Both positions are represented among the most eminent physicists alive. The debate is unresolved, and the inability to resolve it is itself a sign of how deep the crisis goes, because the crisis is not just about what the laws of physics are, but about what counts as an explanation. Let us now confront directly the deepest and most disorienting possibility that modern physics has forced upon us, the possibility that the universe does not have a definite state in the absence of observation. This is the measurement problem, reframed at its most radical. In the Copenhagen interpretation, this is a practical limitation. We say that quantum states do not have definite properties before measurement, but we do not worry too much about what that means for the universe as a whole, because we are always measuring something, always interacting with something, always collapsing wave functions. But what about the universe as a whole? The wave function of the universe, the quantum state of every particle, every field, every degree of freedom in the entire cosmos, is not being observed by anything outside itself. There is no external observer measuring the universe. So what is the state of the wave function of the universe? Does it have a definite state? Is it in superposition? Is it constantly branching in the many-world sense? Or does the concept of a quantum state of the universe not even make sense within the Copenhagen framework that requires an external observer? Quantum cosmology, the attempt to apply quantum mechanics to the universe as a whole, runs immediately into this problem, and there is no consensus on how to resolve it. The universe, the largest physical system there is, the system within which all observations take place, is the one system to which our rules for making sense of quantum mechanics cannot be straightforwardly applied. The Wheeler-DeWitt equation is the equation that quantum cosmologists write down when they try to describe the quantum state of the universe. It is derived by applying the principles of quantum mechanics to general relativity at the level of the entire cosmos, and it is one of the most profound and most confusing equations in physics. It describes the quantum wave function of the universe, the superposition of all possible spatial geometries, all possible matter configurations, all possible universe histories, and it has a feature that is immediately, devastatingly strange. Time does not appear in it. The Wheeler-DeWitt equation has no time dependence, it is a static equation. The wave function of the universe does not evolve in time, it just is. This is the problem of time in quantum gravity. The fact that when you try to combine quantum mechanics with general relativity at the level of the whole universe, time disappears from the equations. In ordinary quantum mechanics, physical systems evolve in time, their wave functions changing from moment to moment according to the Schrödinger equation. But in quantum cosmology, there is no background time for the universe's wave function to evolve against. Time in general relativity is not an external background. It is part of the dynamic structure of space-time, which is itself quantized. And in a fully quantum description of the universe, there is no classical time, no external clock, no before and after. Time, as you experience it, as the dimension along which the moments of your life are strung like beads on a wire, may itself be an emergent phenomenon, a property that appears only when you look at certain subsystems of the timeless quantum universe from the perspective of other subsystems that serve as clocks. Time may not be fundamental. It may arise the way temperature arises, from the coarse-grained perspective of systems that are too large and too classical to perceive the timeless quantum reality underneath. The prospect that time is not fundamental, that it is emergent, approximate, observer-dependent, should stop you in your tracks, because time is not just a feature of physics, it is the structure of all experience. Every thought you have unfolds in time. Every memory, every anticipation, every sense of the present moment as distinct from the past and the future, all of it depends on time existing as a real, objective feature of the world. If time is emergent, then in some sense your experience, the continuous flowing, temporally structured experience of being a conscious entity, is built on something that is not, at the deepest level, real. It is built on an approximation, a useful fiction that holds together at the macroscopic scale, but dissolves at the quantum gravitational foundation. This does not mean your experience is an illusion in any simple sense. It means the relationship between the experience of time and the fundamental structure of the universe is not what it intuitively seems to be. You are not riding a river. You are a pattern in a structure from which the appearance of a river emerges, and the appearance is so perfect, so complete, so self-consistent that you could spend an entire lifetime inside it without ever noticing that the river is not quite there, until you look at the equations. The question of consciousness and its relationship to the physical universe is one that physics has generally tried to avoid, and for good reason. It is extraordinarily difficult to study rigorously, and it is easy to slide from science into speculation without noticing the transition. But certain features of quantum mechanics make the question unavoidable. The measurement problem, at its core, involves an observer. The wave function collapses, acquires definite values in the context of measurement. And measurement, ultimately, is not just a physical process, but a cognitive one. It is the acquisition of information by an observer, who then knows something they did not know before. Does the observer need to be conscious? Most physicists say no, that any physical interaction that records information constitutes a measurement, whether or not a conscious mind is involved. But this answer, while pragmatically satisfying, does not fully dissolve the problem, because it simply pushes the question back one step. What counts as a physical interaction that records information? What distinguishes a measurement from any other physical interaction? Every particle in the universe is constantly interacting with every other particle in its vicinity. Why do only some interactions count as measurements? Why does only some subset of physical processes cause wave function collapse, or branching, or whatever the correct description of the transition from quantum to classical actually is? Nobody has a fully satisfying answer. And the fact that consciousness is the most obvious, most natural candidate for the thing that makes a measurement, even if most physicists resist that conclusion, means that the question keeps returning, refusing to be permanently settled, hovering at the edge of every serious discussion of quantum foundations. Roger Penrose has proposed, in collaboration with the anesthesiologist Stuart Hameroff, a specific mechanism by which consciousness might be connected to quantum mechanics. Their orchestrated objective reduction hypothesis, ORC-OR, suggests that consciousness arises from quantum computations occurring in structures called microtubules inside neurons, and that these quantum computations involve a physical collapse of the wave function that is governed by quantum gravity, that the objective reduction of the quantum state is a gravitational effect, occurring when the superposition of space-time geometries reaches a threshold determined by the Planck scale. Consciousness, in this view, is not an epiphenomenon riding on top of classical brain processes, but a fundamental feature of the universe, rooted in quantum gravitational physics at the deepest level of physical reality. ORC-OR is controversial. Most neuroscientists and many physicists are skeptical, but it has not been definitively refuted, and it points to a possibility that the deepest unresolved problem in physics and the deepest unresolved problem in biology and philosophy may be the same problem, approached from different sides. The mystery of quantum measurement and the mystery of consciousness may not be two separate mysteries, but one. The philosopher David Chalmers calls it the hard problem of consciousness, the question of why and how physical processes give rise to subjective experience. Why is there something it is like to be you? Why does the electrochemical activity of your neurons produce not just behavior and information processing, things that could in principle be described entirely in the third person, in the objective language of physics and chemistry, but also a first-person experience, a qualitative feel, the specific and intimate quality of seeing red or feeling pain or hearing music? This is not the same as asking how the brain processes information. We know a great deal about that, and we are learning more. This is asking why any physical process, no matter how complex, produces experience at all. Why does the universe not just process information in the dark, with no inner light of awareness. What is the relationship between the objective, third-person description of the physical world and the subjective, first-person reality of experience? This question has not been answered, not approximately, not in outline. It has not been answered at all, and some philosophers and scientists like Chalmers himself believe that no amount of neuroscience or physics will ever answer it because it asks something that lies outside the domain of any third-person empirical science. Others, like Daniel Dennett, argue that the hard problem is an illusion, that when we fully explain the functional and informational processes of the brain, the mystery of consciousness will dissolve. But even Dennett's position requires an explanation of why the mystery feels so real, why it seems so obviously that there is something it is like to be you, even if that seeming is itself a product of information processing. The feeling of the mystery is itself part of the data. Some physicists and philosophers have taken the radical step of suggesting that consciousness is not produced by matter at all, that it is, in some sense, fundamental. Panpsychism, the view that some form of experience or experiential quality is a basic feature of reality, present at all levels of physical organization, is having a genuine philosophical revival, not the naive cartoon version of panpsychism in which rocks and electrons have rich inner lives, but more sophisticated versions in which something like the capacity for experience, some proto-experiential quality, is a fundamental feature of the universe in the way that mass or charge is fundamental, and that complex experience, human consciousness, arises from the combination and integration of these simpler experiential properties in complex physical systems. This view is taken seriously by a number of eminent philosophers, including Galen Strawson, Philip Goff, and arguably, in his later work, David Chalmers. It is not mainstream in physics, but it is a logical response to a genuine problem. If consciousness cannot be derived from non-conscious physical stuff by any known or conceivable mechanism, and if consciousness is clearly real, then perhaps the solution is not to explain consciousness in terms of matter but to revise our concept of matter, to include something experiential at its foundation. Perhaps the universe is not a collection of unconscious particles that somehow accidentally produces minds. Perhaps mind in some primitive form is woven into the structure of things from the beginning, and if it is, then every measurement in quantum mechanics, every collapse of the wave function, every observation that turns a quantum shimmer into a classical fact, is not just a physical event but a moment of experience, a moment in which the universe knows something about itself. Whether or not panpsychism is correct, the possibility it represents, the possibility that the categories we use to divide the world into mind and matter, into observer and observed, into consciousness and physics, may be inadequate to describe what is actually there, is one that modern physics increasingly forces us to take seriously. The division between subject and object that has been the operating assumption of science since Descartes, the idea that there is an objective world out there, independent of any observer, and that science is the method for discovering that world's properties, is precisely what quantum mechanics undermines. The observer cannot be cleanly separated from the observed. The measurement apparatus cannot be fully described independently of what it measures. The wave function, which is supposed to be the complete description of a quantum system, depends on the frame of reference of the observer in ways that challenge the idea of an observer-independent reality. And if there is no fully observer-independent reality, if reality is in some ineliminable sense relational, defined by interactions and relationships rather than absolute intrinsic properties, then the scientific project of describing the world as it is in itself, independent of any observer, may be approaching a fundamental limit, not because science is failing, but because reality may not be the kind of thing that has observer-independent properties to discover. Carlo Rovelli, the Italian physicist who developed loop quantum gravity and who writes with unusual clarity and philosophical depth about the foundations of physics, has developed a view he calls relational quantum mechanics, in which the quantum state of a system is not a property of the system, but a property of the relationship between the system and another system, an observer, in the most general sense. In this view, there is no such thing as the absolute state of an electron. There is only the state of the electron relative to this detector, or relative to that measuring device, or relative to the rest of the universe as seen from a particular vantage point. Different observers can have different incompatible quantum states for the same system, and all of them are equally correct, not as approximations to some underlying true state, but as complete, valid descriptions from their respective perspectives. Reality in relational quantum mechanics is not a collection of things with intrinsic properties. It is a network of relations, a web of interactions, in which properties exist only in the context of those interactions and have no meaning in isolation. This is a universe in which being is always being in relation to, never simply being. A universe in which the old dream of the detached objective observer, standing outside the system describing it from nowhere, is not just impractical, but incoherent. What makes Ravelli's view and the broader relational picture of quantum mechanics particularly striking is how well it resonates with the holographic principle and with the emerging picture of space-time as arising from entanglement. In all of these frameworks, what is primary is not things but relationships, not objects but information, not substance but process. The universe begins to look not like a collection of billiard balls bouncing around in a fixed container, but like a vast, self-referential process. A web of correlations and relationships that generate the appearance of objects in space and time as emergent, higher-level descriptions. Reality in this picture is less like a thing and more like a language, a structure of relationships that refers to itself, generates its own meaning, and exists not as a static object, but as an ongoing process of self-organization and self-description. And the observers, the minds that perceive and measure and theorize, are not external to this process but are themselves part of it. Nodes in the web, points where the universe becomes aware of its own structure and generates descriptions of itself that are always inevitably partial, perspectival, and incomplete. The incompleteness of every description is not a failure of science. It is, as the mathematician Kurt Gödel showed in 1931, a necessary feature of any sufficiently powerful formal system. Gödel's incompleteness theorems proved that any consistent mathematical system complex enough to describe arithmetic must contain statements that are true but unprovable within that system, that no sufficiently rich formal system can be both complete and consistent, that there will always be truths that lie outside the reach of any given set of axioms. This result, which sent shockwaves through the mathematical world when it was first published, has been interpreted in many ways. Some interpretations are too broad. Gödel's theorem says things about formal systems, and its application to physics or to human knowledge in general requires careful argument. But there is a legitimate sense in which Gödel's result, when applied to the universe as a formal system, as a structure that, if the computational picture of reality is correct, is in some sense computing itself, suggests that the universe may contain truths about its own nature that cannot be derived from within itself by any internal process. There may be facts about the universe that are true, that are real features of physical reality, but that are in principle inaccessible to any observer embedded in that reality. Not just practically inaccessible, not just beyond the reach of current instruments, but fundamentally, logically, permanently unknowable from the inside. The experimental anomaly that arguably cuts deepest into the current moment, the one that has generated the most intense and most recent discussion among working physicists, is the persistent tension between the predictions of the standard model of particle physics and the results of certain precision measurements. The standard model is the quantum field theory that describes all known fundamental particles and three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force, and it is extraordinarily successful. It predicted the existence of the Higgs boson before it was discovered, and its predictions have been verified to extraordinary precision in experiments at the Large Hadron Collider and elsewhere. But in 2021, the muon G2 experiment at Fermilab announced a measurement of a quantity called the magnetic moment of the muon, a heavier cousin of the electron, that deviated from the standard model's prediction with a statistical significance of 4.2 sigma. In particle physics, 5 sigma is the conventional threshold for a discovery. A 4.2 sigma deviation is not yet definitive, but it is the kind of result that physicists pay very serious attention to. If it holds up as more data are collected and analyzed, it would be direct evidence that there are particles or forces in the universe that the standard model does not account for, that beyond the currently known particles, there is more, something new, something that is already affecting the behavior of muons in ways that our best theory cannot explain. The muon G2 result is exciting precisely because it is specific and quantitative. It is not a vague anomaly or an unexplained observation, but a precise numerical discrepancy between theory and experiment of the kind that historically has led to the discovery of new physics. The electron's anomalous magnetic moment was once a similar discrepancy, and its resolution led to the development of quantum electrodynamics, one of the most successful theories ever constructed. The hope is that the muon's anomalous magnetic moment will similarly point toward a new and deeper theory, perhaps supersymmetry, which predicts a partner particle for every known particle, perhaps extra dimensions, perhaps new force-carrying particles beyond the W and Z bosons and the gluons that mediate the known forces. The Large Hadron Collider has been searching for supersymmetric particles since it began operation and has not found them. The energy scales at which supersymmetry was originally expected to emerge have been ruled out, but the parameter space is large, and the absence of discovery at the LHC does not mean the theory is wrong. It may mean the new particles are heavier than the LHC can reach, or that they couple to standard model particles in ways that make them harder to see. The search continues, the anomaly remains, and the standard model, for all its success, has a growing number of places where it does not quite fit the universe it was built to describe. There is also the matter of neutrino masses. The standard model, as originally constructed, predicted that neutrinos, the lightest and most ghostly of the fundamental particles, electrically neutral, interacting only through the weak force and gravity, produced in enormous quantities by the sun and by nuclear reactions, have exactly zero mass. They were predicted to travel at the speed of light, to never slow down, to be the closest thing in the particle zoo to nothing. And then, in 1998, the Super Kamiokande experiment in Japan measured something that the standard model said could not happen: neutrinos oscillating between their three types, or flavors. A neutrino produced as an electron neutrino was detected as a muon neutrino after traveling a certain distance. This flavor oscillation is only possible if neutrinos have mass. If different neutrino mass eigenstates travel at slightly different speeds and interfere with each other in a quantum mechanical process, analogous to the beating of two sound waves of slightly different frequencies. The measurement was clear and reproducible. Neutrinos have mass. The standard model is wrong. Not catastrophically, not in a way that invalidates all of its successes, but structurally wrong, missing a basic feature of the particles it is supposed to describe. The standard model has been patched to accommodate neutrino masses, but the origin of those masses, why they are so much smaller than the masses of all other massive particles, what mechanism generates them, remains unknown. It is one more parameter that the theory cannot predict, one more place where the map does not quite match the territory. The discrepancies accumulate, the anomalies multiply, and in their accumulation they begin to suggest not a collection of unrelated puzzles but a pattern, a picture of a theory that is extraordinarily successful within a certain domain of validity, but that is showing at its edges the signs of something beyond itself, some deeper structure that it approximates but does not capture. The standard model is to the next theory what Newtonian mechanics was to relativity, not wrong in any way that shows up in everyday calculations, but missing the depth and breadth of a more complete description that includes phenomena it cannot account for. The question is what the next theory is, and here, unlike the transition from Newton to Einstein, the physics community does not have a clear candidate. The transition from Newtonian to Einsteinian physics was guided by specific experimental results, the null result of the Michelson-Morley experiment, the anomalous precession of Mercury's orbit that pointed clearly toward the needed revision. Today, the anomalies are more numerous but less focused. They point in different directions. The muon G2 anomaly points one way, the Hubble tension another, the cosmological constant problem another, the information paradox another. It is as if the map of physics is showing cracks in many places simultaneously, suggesting not a localized problem in one wall of the edifice, but something wrong with the foundation, but without making it clear exactly where in the foundation the problem lies. Some of the most creative thinkers in theoretical physics have begun to suggest that the problem may be even deeper than finding the right theory, that it may require finding the right language in which to formulate a theory. Every theory in physics is written in mathematics. The extraordinary effectiveness of mathematics in describing the physical world, what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics in a famous 1960 essay, is itself one of the deepest puzzles in the philosophy of science. Why should the abstract structures developed by mathematicians, often with no thought of physical application, turn out to describe the behavior of the physical world with uncanny precision? Why should group theory, developed by pure mathematicians studying abstract symmetries, turn out to be exactly the right tool for classifying elementary particles? Why should differential geometry, invented by mathematicians studying curved surfaces, turn out to be exactly the right language for general relativity? Why should complex analysis, developed for purely mathematical reasons, turn out to be indispensable in quantum mechanics? The match between the structures of pure mathematics and the structures of physical reality is so consistent and so precise that it demands explanation. And the most natural explanation, and the one that follows most directly from the evidence, is that the universe is, in some sense, mathematical, that the physical world does not merely follow mathematical laws, but is, at its deepest level, a mathematical structure, with physical objects being nothing but abstract mathematical entities, and physical existence being nothing but mathematical existence. This is the mathematical universe hypothesis, most fully articulated by the cosmologist Max Tegmark, and it is one of the most radical ideas that a serious physicist has proposed in recent years. Tegmark argues that if the universe is completely described by a mathematical structure, if there is a mathematical structure that captures every feature of physical reality, then there is no meaningful distinction between that mathematical structure and the physical universe. The universe is not described by mathematics. The universe is mathematics. All mathematical structures exist in the same sense that our universe exists, and the reason we find ourselves in this particular mathematical structure is anthropic. It is one of the structures that contains observers complex enough to ask the question. If Tegmark is right, then the deepest question, why does the universe exist, and why does it have the particular laws it has, dissolves into a tautology. All possible mathematical structures exist, and we are in one of them. There is no deeper explanation. There cannot be. The multiverse is not a collection of physical universes somehow produced by some metaphysical process. It is the ensemble of all mathematical structures, all existing with equal ontological status, and physical existence is simply mathematical existence perceived from the inside by sufficiently complex self-referential structures within those mathematics. This is an extraordinary idea. It is also completely untestable by any conceivable experiment, and the fact that it is untestable is not simply a practical limitation, but may be a principled one. If every mathematical structure is equally real, then there is no experiment that could distinguish between them, because every possible experimental result occurs in some structure. The mathematical universe hypothesis may be true, and it may be permanently beyond the reach of science to confirm or deny. We are now in territory where the boundary between physics and philosophy becomes difficult to locate, and that is itself one of the most significant things about the current moment in science. For most of the 20th century, physics and philosophy maintained a polite but increasingly distant relationship. The logical positivism of the Vienna Circle had declared that any meaningful statement must be verifiable by experience, and questions that could not in principle be answered by experiment were dismissed as meaningless pseudo-questions. Physics took this stance seriously. Many physicists adopted the attitude, sometimes called shut up and calculate, that the job of physics is to make correct predictions and leave questions about what the predictions mean to philosophers who, in the physicists' view, were not constrained by the discipline of experimental accountability. For a while this worked. The predictions kept working. The technology kept advancing. The experiments kept confirming the theories. But the cracks in the foundations kept growing, and the questions that had been dismissed as philosophical kept turning out to be physically consequential. The question of what quantum mechanics means, which was supposedly just philosophy, turns out to determine whether information is preserved in black holes, which is a concrete physical question. The question of what time is, supposedly just metaphysics, turns out to determine whether a theory of quantum gravity is even formulable. The question of what counts as an observer, supposedly just semantic, turns out to determine the resolution of the measurement problem, which is the deepest open question in quantum foundations. Philosophy crept back in through the cracks, because the cracks were large enough to require it. The most unsettling development of recent years, the one that perhaps best illustrates the degree to which reality is behaving in ways that our frameworks cannot contain, involves the experimental verification of something called quantum contextuality. Contextuality is a feature of quantum mechanics that says the outcome of a measurement can depend not just on the system being measured, but on which other measurements are being made simultaneously. This sounds technical, and it is, but its implications are profound. It means that quantum systems do not have definite properties that pre-exist their measurement. It means that the question, what is the spin of this particle, does not have a definite answer that the particle is carrying around with it, waiting to be discovered. The answer depends on the context, on what else is being measured, on how the question is being asked. And this is not just a matter of practical limitation or disturbance by the measuring apparatus. It has been proved mathematically, in theorems by Simon Cohen and Ernst Specker, and later strengthened by many others, that no hidden variable model, No model in which particles have pre-existing definite values for all measurable quantities can reproduce the predictions of quantum mechanics. The universe, at its quantum level, is irreducibly contextual. Properties do not exist until they are measured, and which property comes into existence depends on the context of measurement. Reality, at its deepest accessible level, is not a collection of facts waiting to be discovered. It is a collection of potentials that become facts in the context of interaction. A universe of possibilities that crystallize into actualities only in the presence of other actualities. It is a universe that is, in a very precise technical sense, not entirely real in the absence of observation. What does it mean for something to not be entirely real in the absence of observation? The question sounds like it belongs in a meditation retreat or a philosophy seminar, not in a laboratory. And yet the laboratory, the most rigorous, most skeptical, most committed to the facts institution that human civilization has devised, is precisely where this conclusion has been forced upon us. The experiments of Bell, Aspect, Clauser, Zeilinger, and dozens of their colleagues, repeated and refined over 50 years, have systematically closed every loophole, eliminated every alternative explanation, and confirmed what the mathematics of quantum mechanics predicted. The world is not locally real. The particles do not have definite values before measurement. The measurement outcomes are not determined by pre-existing hidden information. Something genuinely comes into being at the moment of measurement that was not there before, not as a discovery of something previously existing, but as a creation of something previously potential. And this happens everywhere, all the time, at the level of every quantum interaction, which is to say at the level of every interaction period, because all interactions are ultimately quantum interactions. The classical world of definite objects and definite properties that you experience is not the fundamental world. It is the world that emerges when quantum potentials are realized in the context of large, complex, decohered systems. And the process of decoherence, the mechanism by which quantum superpositions are suppressed and classical behavior emerges, does not solve the measurement problem. It only disguises it. The superposition does not vanish. It spreads, growing larger and larger, entangling more and more systems until it encompasses the entire environment. The measurement apparatus, then the laboratory, then the planet, then the universe, all become entangled with the quantum state of the original particle. But the entanglement does not produce a definite outcome. It produces a larger superposition. And the question of why you experience one definite outcome rather than the superposition, the question of why the world appears to have a fact of the matter, remains unanswered. Perhaps the most haunting experimental result of recent years, one that has not received the mainstream attention it deserves, is the so-called delayed choice quantum eraser experiment, which is a more elaborate version of the double-slit experiment that tests what happens when information about a particle's path is created after the particle has already been detected. The setup is intricate, but the logic is clear. Two entangled photons are produced. One of them, the signal photon, is sent toward a double-slit apparatus and detected at a screen. The other, the idler photon, is sent on a longer path that gives it the opportunity to either retain or lose the witch path information about its entangled partner. If the idler photon's path information is preserved, if there is any way, even in principle, to determine which slit the signal photon went through by measuring the idler, then no interference pattern appears for the signal photons. If the idler photon's witch path information is erased, if the measurement of the idler is set up so that no witch path information can be extracted, then an interference pattern reappears in the signal photons. And here is the part that makes the mind go quiet with a very specific kind of vertigo. The idler photon's path is longer. The signal photon is detected first. And yet whether an interference pattern appears in the signal photons, the pattern on the screen that the signal photon has already hit, depends on what is done to the idler photon afterward. The future behavior of the idler photon appears to affect the past behavior of the signal photon. Or more precisely, the correlations in the data, assembled after both photons have been detected, show that whether the signal photon behaved like a wave or behaved like a particle depends on what happened to its entangled partner after the signal photon had already landed. The result is assembled by comparing timestamps and can only be seen in retrospect, so no information travels backward in time. But the correlations themselves are structured as if the future is shaping the past, as if the choices made later are somehow reaching back and influencing what already happened. The delayed choice quantum eraser does not truly allow backward causation. Information cannot actually be transmitted from future to past in any way that violates relativity. but it does something almost as disturbing. It reveals that the concept of what happened at the double slit, whether the photon went through one slit or both, does not have a definite answer independent of what is measured later. The photon's past does not have a definite observer-independent history until the entire experimental context, including future measurements, is fixed. The past is not settled. The history of a quantum particle is not written in stone at the moment events occur, but is, in some sense, open to revision based on subsequent choices and measurements. This is not time travel. This is something stranger. It is the suggestion that the fabric of events, the sequence of what happened and when, is not as definite, not as fixed, not as irreversibly written as you have always assumed. The past you remember is real. The events of your life occurred. But the past of a quantum particle, before it is connected to a network of classical records and measurements, may be as indeterminate as its future. Time, history, the settled givenness of what has already occurred, all of it becomes, at the quantum level, negotiable. And now you have to sit with all of this. Not just the individual anomalies and paradoxes and measurement problems, but the cumulative weight of all of them together. The wave function and its collapse, the non-locality of entanglement, the incompatibility of quantum mechanics and general relativity, the Hubble tension, the cosmological constant problem, the dark matter mystery, the information paradox, the arrow of time, the problem of consciousness, the delayed choice quantum eraser, the contextuality theorems, the holographic principle, the emergent nature of spacetime, the mathematical universe, the simulation hypothesis, the underdetermination of quantum interpretations, the incompleteness of the standard model, the mystery of neutrino masses, the inaccessibility of the Planck scale, the horizon problem, the eternal inflation multiverse, the Wheeler-DeWitt equation, and the disappearance of time, the hard problem of consciousness, the unreasonable effectiveness of mathematics, Gödel's incompleteness. None of these is a minor puzzle. Each is, on its own, a profound challenge to the picture of reality that science and common sense have collaboratively built over centuries. Together, they are something else. Together, they are a pattern, and the pattern says something is wrong. Not wrong in the way that any particular theory is wrong. Wrong in a more fundamental way. Wrong in the way a map is wrong when the territory it is supposed to describe is not the kind of thing that can be mapped. Think about the nature of a map. A map works because the territory it represents has a definite structure, definite geography, definite distances, definite relationships between locations. A map of a city is possible because the city has a definite layout that exists independently of anyone looking at it. The map can be more or less accurate, more or less detailed, but the existence of an accurate map is possible because there is a fact of the matter about how the city is arranged. What modern physics is beginning to suggest, not with certainty, not with consensus, but with an increasing weight of evidence and theoretical argument, is that the universe may not be the kind of territory that has a map. Not because the territory is too complex or too large to map completely, but because the territory is the kind of thing that comes into existence in the process of being mapped. A universe in which measurement creates rather than discovers, in which properties are relational rather than intrinsic, in which space-time emerges from entanglement rather than being a fixed container, in which consciousness may be irreducibly woven into the act of observation. Such a universe does not have a definitive, observer-independent layout waiting to be charted. It is constituted by the act of observation, shaped by the act of measurement, defined by the web of interactions that structure it. And a map of such a universe would not be a picture of something that exists independently of the mapping. It would be a participant in the territory it describes. It would be part of what it maps. This is where the psychological journey that physics has taken us on arrives at its most vertiginous point, not at a cliff edge from which you can see the abyss clearly, but at a place where the ground beneath your feet becomes uncertain in a way that is hard to locate precisely, a way that makes each step feel slightly less solid than the last. You began, thousands of words ago, in a world that felt solid and knowable, a world governed by definite laws, described by reliable theories, navigable by the light of human reason, and step by step, experiment by experiment, paradox by paradox, that solidity has been quietly eroded, not replaced by nothing. The theories still work, the predictions still succeed, the technology still functions, but the meaning of that success has become ambiguous. The theories work without anyone knowing what they mean. The predictions succeed without anyone knowing what they are predictions about. The technology functions without the physicists who designed it being able to agree on what is happening at the level of fundamental reality. The success of science has never been in doubt. What is in doubt is what the success is revealing. The physicist Richard Feynman, one of the greatest intuitive thinkers in the history of physics, famously said that if you think you understand quantum mechanics, you do not understand quantum mechanics. This was not false modesty. It was a precise statement about the state of knowledge. Quantum mechanics can be used. Its formalism is unambiguous. Its predictions are definite. Its applications are everywhere. But what it means and what the world is actually like at the quantum level is a question that Feynman himself could not answer, and that remains open today, decades after his death. The formalism works. The world behind the formalism is opaque. And the gap between working and understanding is not a technical gap that more time and more experiments will close. It is a conceptual gap, a gap in our frameworks for thinking about what it means for something to exist, what it means for something to happen, what it means for something to be real. These are not scientific questions in the conventional sense, but they are questions that science has forced us to confront. By building a theory that works perfectly without answering them, what do we do with this? The human mind, confronted with deep uncertainty, has several options. It can retreat into denial, pretend the questions are not as serious as they are, focus on the practical success of the theories, and leave the foundations to philosophers who can worry about them in comfortable obscurity. This is what most working scientists do most of the time, for the very practical reason that you cannot do physics while being perpetually paralyzed by foundational anxiety. It is a reasonable, pragmatic choice, but it is not an answer. The questions do not go away because you choose not to look at them. The universe does not resolve its own anomalies because we find them inconvenient. The second option is to embrace the uncertainty, to see the openness of these questions not as a failure of science but as a frontier, the most exciting and most important frontier in the history of human inquiry. The questions that remain open are not leftover puzzles, loose threads at the edge of a tapestry that is otherwise complete. They are the center. They are the questions whose answers would transform our understanding of reality more completely than any discovery in human history. What is the universe at its most fundamental level? What is consciousness? What is time? What is information? Why does anything exist rather than nothing? These are not questions science has answered and filed away. They are questions science has made more precise, more urgent, and more genuinely mysterious than at any previous point in human history. There is a third option, and it is the most difficult. It is to sit with the uncertainty without resolving it, to let the strangeness of the universe be strange, to resist the temptation to package it into a neat narrative of progress or crisis, to hold open the space in which genuinely new thinking might emerge. The history of physics shows that the greatest advances have not come from solving the problems of the existing framework on its own terms, but from stepping outside the framework altogether, from seeing that the framework itself embeds assumptions that seem so obvious as to be invisible, and questioning those assumptions. Newton's physics embedded the assumption of absolute time, a time that flows at the same rate for all observers everywhere. Einstein questioned that assumption and discovered relativity. Classical physics embedded the assumption that physical systems have definite states, independent of measurement. The founders of quantum mechanics questioned that assumption and discovered the quantum world. What assumptions are embedded in our current framework so deeply that we do not even see them as assumptions? What invisible axioms are limiting our ability to formulate the right questions, let alone find the right answers? Some physicists suspect that one of those assumptions is the assumption that the universe can be described from the outside, that there is a view from nowhere, a God's eye perspective from which the complete state of reality can be specified and its evolution calculated. Every physical theory we have is formulated this way. There is a state of the system, there are laws governing its evolution, and an observer uses those laws to predict future states, but in a universe that is itself a closed system with no external observer. In a universe in which the observer is always inside the system being described, the very structure of physical theory may be inappropriate. Wheeler's participatory universe, Ravelli's relational quantum mechanics, the holographic principle, the computational universe, all of these, in their different ways, take seriously the idea that description is always from the inside, always perspectival, always partial, and that a complete observer-independent description of the universe may not be a coherent concept. If this is right, then the next revolution in physics will not be a new theory written in the same old mathematical language about the same old objects. It will be a new way of thinking about what a physical theory is, what it is supposed to describe, and what it means for a description to be complete. There are researchers working on exactly this, not on solving the current theory's problems, but on finding new conceptual foundations from which better theories might grow. The field of quantum information theory has suggested that information, rather than matter or energy, might be the primitive concept from which physics should be built, and from that seed, a small but growing community of physicists has been attempting to reconstruct quantum mechanics from scratch, deriving its formalism not from historical accident and experimental necessity, but from a small set of simple, conceptually clear axioms about information and its processing. The results have been striking. Several groups have independently shown that many of the strange features of quantum mechanics, the uncertainty principle, the existence of superposition, the impossibility of cloning quantum states, the non-locality of entanglement, can be derived from information theoretic axioms without assuming anything about particles or waves or Hilbert spaces or any of the other mathematical machinery that quantum mechanics traditionally begins with. This suggests that the strangeness of quantum mechanics is not arbitrary, not the result of some bizarre accident in the structure of nature, but the necessary consequence of something deeper, something about the way information can be structured, processed, and shared in a universe where observation is always partial and perspectival. The quantum world is strange not because the universe is perverse, but because information, at its most fundamental level, behaves in ways that are more subtle and more constrained than our classical intuitions assume. And if that is right, then the next physics, the physics that unifies quantum mechanics and gravity, that resolves the measurement problem, that explains the cosmological constant and dark energy and the arrow of time, will be written in the language of information, not in the language of particles and fields. But we are not there yet, not even close. The new language is being invented word by word in papers and conferences and late-night calculations by people who are not sure they are on the right track, but who are too troubled by the current situation to stay on the old one. And in the meantime, the anomalies accumulate. The measurements refuse to agree. The theories refuse to unify. The universe continues to behave in ways that should not be possible, quietly and persistently, and without any apparent concern for the distress this causes to the minds that are trying to understand it. Every new experiment is a test of the current framework, and the framework keeps passing those tests in some ways while failing them in others, like a building that passes the fire inspection, but has cracks in its foundation that the inspectors do not have instruments to measure. The building stands, the people inside it go about their lives, and somewhere below, in the place where the foundation meets the bedrock of reality, something that cannot quite be heard and cannot quite be felt and cannot quite be seen is nevertheless, unmistakably, moving. You have been living your entire life in that building. You have walked its corridors and trusted its walls and looked out its windows at a world that seemed solid and knowable and governed by rules that, even when complicated, were at least in principle understandable. The sun rises, objects fall, causes precede effects. The past is settled, the future is open. The things around you are made of matter, and matter is made of atoms, and atoms are made of particles, and the particles follow laws, and the laws are knowable. This is the world your nervous system evolved to navigate. This is the world your language was built to describe. This is the world that felt, until perhaps recently, like enough, like all there was, like reality, plain and simple and dependable. And now the cracks are showing. Not in the walls you can see, not in the surfaces you touch, but in the foundations that everything rests on. In the deepest descriptions of what matter is, what space is, what time is, what observation is, what existence is. The cracks are invisible to the naked eye. They show up only in the most precise measurements, only in the most abstract mathematics, only in the conversations of people who have spent their lives looking harder at reality than most people know is possible. But they are there. They were there before anyone noticed them. They will be there long after this moment has passed. And the question they pose is one that cannot be answered by any current theory, by any current instrument, by any current framework for thinking about what the universe is and how it works. The question is not what is the anomaly. There are many anomalies, and they have been described. The question is not what is the solution. There is no agreed solution, and the search continues. The question is something more fundamental, something that underlies all the specific puzzles and paradoxes and tensions and discrepancies. The question is whether the universe is the kind of thing that can be fully known, fully described, fully understood by minds that are inside it, made of it, shaped by it, limited by it. Whether the act of understanding is limited by the thing being understood in a way that is not just practical, but principled. Whether there is a ceiling to knowledge that is built into the structure of reality itself, not because reality is hiding anything, not because it is protecting a secret, but because complete self-knowledge may be something the universe, like Gödel's formal systems, is structurally incapable of achieving from the inside. Whether the map can ever fully describe the territory when the mapmaker is part of the territory being mapped. Think about that for a moment. Really think about it. You are a process that the universe is running, a pattern of matter and energy and information that has organized itself over billions of years of cosmic and biological evolution into something complex enough to ask questions about the nature of the universe. You are the universe becoming aware of itself, in the phrase that is sometimes attributed to Carl Sagan and sometimes to others, and that belongs really to no single person because it is simply true. And the questions you are asking, the ones that physics has sharpened to a point sharp enough to cut, are questions that the universe is asking about its own nature through you. The strange loop of this, a universe questioning itself through the minds it has produced, using tools and languages those minds have invented, arriving at answers that are always incomplete because the questioner and the questioned are the same, is not just poetic. It is the actual epistemic situation of every physicist who has ever lived. Every equation ever written was written by a part of the universe trying to describe the whole from the inside. Every measurement ever made was made by a piece of the universe probing another piece of the universe with instruments that are themselves pieces of the universe. There is no outside. There is no neutral ground. There is no view from nowhere. There is only this, awareness inside a mystery, looking outward and finding the mystery looking back. The measurements will continue. New experiments will be designed. New data will be collected. New anomalies will be discovered and new paradoxes will emerge. The Large Hadron Collider will continue operating and may eventually produce results that demand a revision of the Standard Model. The next generation of cosmic microwave background experiments may sharpen the Hubble tension to the point where it becomes undeniable that something is missing from the standard cosmological model. New gravitational wave detectors may reveal features of the space-time fabric that current theory cannot account for. Quantum computers, as they scale to larger and larger systems, may reveal new aspects of the quantum classical boundary and force the question of decoherence and measurement into a new and more experimental domain. Dark matter searches may eventually find something, or the absence of any signal may eventually become so complete that the particle hypothesis must be abandoned and new directions pursued. The James Webb Space Telescope, peering back to within a few 100 million years of the Big Bang, has already returned images that have surprised cosmologists. Galaxies that are larger, more structured, more fully formed than standard models predict for that early epoch of the universe, suggesting that either galaxy formation proceeded faster than expected, or the timeline of the early universe is not quite what we thought. Each of these developments will add to the picture. Each will add detail, and very likely, each will add mystery. Because this is what the history of physics teaches, even as it records a continuous accumulation of knowledge. Each answer generates more questions than it resolves. Newton explained the motion of planets and opened the question of what gravity actually is. Einstein answered that question and opened the question of what happens at the quantum level of space-time. The founders of quantum mechanics answered many questions about atomic and subatomic behavior and opened the measurement problem, the interpretation problem, the quantum gravity problem, and the information paradox. The Standard Model successfully described all known particles and forces and opened the question of why the parameters of the model have the values they do, what lies beyond the model, and what dark matter and dark energy are. Each layer of understanding reveals a deeper layer of mystery, and there is no guarantee, there is no reason at all to assume that this process converges to a final answer rather than continuing indefinitely, each new depth revealing a further depth below it, an infinite regression of understanding and mystery interleaved without end. And perhaps that is the most important thing to take from all of this, not the specific anomalies, not the named paradoxes and their proposed resolutions, not the tension between this number and that measurement, not the failure of this theory to unify with that theory. All of those are important, and all of them deserve the attention of the finest minds alive, and they are getting it. But the deeper lesson, the one that changes not just what you know but how you know it, not just what you believe but how you believe it, is that reality is stranger than it looks. Much stranger. So much stranger that the distance between the world as it appears and the world as it is may be the most important distance in science. and crossing it may be the defining challenge not just of physics, but of human understanding itself. The world looks solid, and it is mostly empty space. The world looks classical, and it is fundamentally quantum. The world looks three-dimensional, and space-time may be four-dimensional at minimum, and holographically two-dimensional at its foundation. Time looks like it flows, and it may be emergent and perhaps not fundamental at all. Objects look as if they have definite properties, and they do not until they are measured. The universe looks as if it is simply there, independent of observers, and it may be constituted by observation in ways that cannot be cleanly disentangled. None of this is certain. All of it is seriously entertained by serious people on the basis of serious evidence and serious argument, and all of it points in the same direction, away from certainty, away from completeness, away from the comfortable idea that the map and the territory are, even approximately, the same thing. You came here knowing that something was wrong. The title told you, the first sentence told you, and perhaps you came half expecting to be reassured, to be told that yes, there are puzzles, but science is working on them. The anomalies will be resolved, the theories will be unified, the picture will eventually become clear. That reassurance is not available, not because science is failing. It is not failing. It is doing precisely what it is supposed to do, which is to follow the evidence wherever it leads, and to refuse to manufacture comfort where the evidence does not support it. It is not available because the evidence leads to a place that is genuinely uncertain, genuinely open, genuinely unresolved in ways that are not merely technical, but fundamental. The universe has not been explained. It has been described with extraordinary precision and extraordinary success in certain regimes and at certain scales and from certain perspectives. But description is not explanation. Success is not understanding. And precision, taken far enough, reveals not clarity but a deeper, more exquisitely defined mystery. Somewhere right now, in a laboratory underground, shielded from the noise of the surface world by tons of lead and water and rock, a detector is waiting. It has been waiting for months or years. It is waiting for a single event, a single particle interaction that would confirm the existence of dark matter, or discover a new force, or reveal a feature of quantum gravity, or detect a signal from beyond the standard model. The detector is extraordinarily sensitive, the scientists who built it are extraordinarily careful, and the detector is, so far, seeing nothing. Not nothing in the sense of failure, nothing in the sense of an exquisitely measured silence, a silence so precise that it itself carries information. What is not seen is as meaningful as what is seen. The silence of the dark matter detectors is a message, and the message is, whatever dark matter is, it is not here, it is not this. It does not interact in the ways you expected. Look elsewhere. Think differently. Question your assumptions about what you are looking for and why you expected to find it where you looked. The universe is not hiding from you out of malice. It is simply not organized the way you assumed. It is organized according to principles that you have not yet discovered, following rules that you have not yet written, in a language that you have not yet learned. And somewhere else right now, on a mountain in Chile or Hawaii or in the cold darkness of space itself, a telescope is looking back in time. Every photon it captures is ancient, light that left its source millions or billions of years ago, carrying information about the state of the universe at a moment before the Earth existed, before the Sun existed, before the Milky Way had taken its current form. The telescope assembles these ancient photons into images, and the images are compared with the predictions of cosmological models, and the models almost fit, almost, but not quite, not in every detail, not at every scale, not in every measurement. The galaxies are where the models say they should be roughly. The large-scale structure is consistent with predictions broadly. But in the details, in the precise statistics, in the specific measurements that the most careful observers extract from the data, there are tensions, small discrepancies that could be measurement error, or could be the signature of new physics, or could be the first glimpse of a feature of the universe that no current theory predicts. The telescopes keep looking, the models keep being refined, and the discrepancies keep being there, quiet and persistent and patient, waiting for a mind that is prepared to understand them. That mind does not yet exist. This is not an insult to the brilliance of current physicists. It is simply the recognition that the conceptual revolution required to understand what these discrepancies are pointing toward has not yet occurred. Relativity required Einstein. Quantum mechanics required Bohr and Heisenberg and Schrödinger and Dirac and a dozen others, working in a period of extraordinary creativity and extraordinary confusion. The next revolution will require minds that have not yet been born, or that are alive now but have not yet had the insight that will change everything. The moment of seeing, suddenly and clearly, what had always been there, but had never been framed correctly. The moment when the right question is asked for the first time and the answer turns out to have been hiding in plain sight in data that already existed. Every revolution in physics has felt in retrospect inevitable. The answer was always there. The clues were always present, and once you see it, you cannot imagine how it was not seen before. And every revolution has been in its moment genuinely surprising. Not a smooth extension of what came before, but a break, a reconceptualization, a moment when the old framework was not refined but replaced by something that asked different questions, used different concepts, and revealed a different universe beneath the one that had seemed familiar. The next break is coming. It may have already begun, in some paper or some dataset or some half-formed idea in some physicist's notebook that has not yet been connected to the right experiment, or the right mathematical framework, or the right conversation with the right colleague. Or it may be decades away, waiting for an instrument that does not yet exist, or a mathematical tool that has not yet been invented, or a philosophical reframing that has not yet been articulated. The history of physics offers no guarantee of timescale. Newton worked for 20 years on the Principia before publishing. Einstein spent 10 years developing general relativity from the special theory. String theory has been in development for 50 years and has not yet produced its defining experimental prediction. The universe is not on a deadline. It has been here for 13.8 billion years and will be here for trillions more, and it is in no hurry to make itself understood to the brief, fragile, brilliantly curious creatures that have recently evolved on its surface and begun, in the last few centuries, to ask questions about its nature. But you are here now. You are asking now. And the asking, the fact that matter has organized itself into something that can look at the universe and be bewildered by it, that can feel the specific intellectual vertigo of confronting a reality that is stranger than any story ever told about it, that can hold open the question without demanding a premature answer. That is not nothing. That may be everything. Because the universe, whatever it is, has produced you. It has produced minds that can contemplate it, that can be troubled by it, that can feel the specific, almost painful beauty of a question that refuses to be resolved. And whether that is a coincidence or a necessity, whether it is an accident of evolution or a feature of a participatory universe in which observation is woven into the fabric of what exists, the fact of it, the fact of awareness inside a mystery, is the most extraordinary fact there is. So here you are. The measurements are in. The anomalies are real. The theories are broken at their foundations in ways that decades of brilliant work have not repaired. The universe is expanding at a rate that two different instruments cannot agree on. The most successful theory of the microscopic world and the most successful theory of space and time cannot be made to speak to each other. Dark matter fills the cosmos and has never been directly detected. Dark energy drives the universe apart, with a force whose magnitude is off by 120 orders of magnitude from what it should be. Particles behave as waves when no one is watching, and as particles when someone is. Entangled particles communicate correlations across arbitrary distances instantaneously, and without any signal. Information may or may not survive the evaporation of black holes. Time may or may not be fundamental. Space may or may not be emergent. The observer may or may not be necessary for the reality of the observed. Consciousness may or may not be a feature of the universe at its deepest level. The past of a quantum particle may or may not be settled before it is measured. The universe may or may not be one of infinitely many universes. Reality may or may not be computational. The map may or may not be capable of describing the territory when the map maker is inside the territory. None of these questions has been answered. Every one of them is real. Every one of them is currently being worked on by some of the most careful, rigorous, imaginative minds our species has produced. And every one of them, followed far enough, leads to the same place, to the edge of what can be known, to the boundary where the instruments stop working, and the equations produce infinities, and the interpretations dissolve into philosophical ambiguity, and the honest answer to the question, what is the universe really, is, we do not know. We have never known. We have built extraordinary descriptions of extraordinary precision that allow us to predict and to build and to cure and to explore, and those descriptions are genuine and irreplaceable achievements of human civilization. But they are not the territory, they are maps. And the territory, the actual universe in itself as it is, independent of any description or any observation, or any framework or any mind, remains, at its deepest level, as unknown as it was before the first equation was ever written. More unknown, in fact, because now we know the shape of our ignorance, which is much larger and much stranger than we thought. The reality you were born into, the reality that felt solid and lawful and comprehensible, has not been destroyed by any of this. It still functions. The sun still rises. Objects still fall. Antibiotics still work. Airplanes still fly. The macroscopic, classical world that your nervous system navigates is as reliable as it has ever been. But it sits now on a foundation that you know to be uncertain, a foundation of quantum superpositions and relational properties and emergent spacetime and holographic information and unexplained constants and incompatible theories and unanswerable questions. The building stands. The foundation is in question, and the knowledge that the foundation is in question changes something, not about how you move through the world, but about how you understand the world you are moving through. It changes the quality of certainty. It changes the texture of knowledge. It changes the relationship between what you see and what is there. It introduces, at the level of bedrock, a permanent, irreducible, scientifically grounded humility about the nature of things, a humility not of defeat, but of honest reckoning, a humility that makes further inquiry possible by refusing to pretend that inquiry has already found what it has not yet found. Reality has not broken in any way that will prevent you from going about your day. The coffee you will drink this morning will still be hot. The ground you walk on will still be solid. The people you love will still be present. Nothing about the anomalies in the data, the paradoxes in the foundations, the unanswered questions in the depths of physics will touch the texture of your immediate experience. And yet something has changed, something that cannot be unchanged, because you now know, not as an abstract philosophical position, but as a concrete, experimentally grounded fact, that the reality you experience is not the whole of what is there, that beneath the surface of the familiar world there is a quantum reality that does not behave like anything you have ever seen, governed by rules that no one fully understands, described by a mathematics whose physical meaning is genuinely disputed, pointing toward a structure of existence so unlike the everyday world that our language barely has words for it. And beneath that quantum reality, at the Planck scale where quantum mechanics and gravity should meet but cannot, there is something else, something that no existing theory correctly describes, something from which space and time and matter themselves emerge, something that may be informational or holographic or geometric or computational or something that has not yet been named because the concepts needed to name it have not yet been invented. You are standing at the surface of something immeasurably deep. You have always been standing here. The difference is that now, for a moment, you can feel it, the depth beneath your feet, the vastness of what is not known, the genuine and scientifically verified strangeness of the universe you inhabit. Most of the time, the feeling is not available. Most of the time, the familiar world closes over it like water closing over a stone, and the depth becomes invisible, and the surface feels like everything. But it is not everything. It is a surface, and below it, the mystery continues, unnamed and unmeasured and in many places unmeasurable, exactly as strange as the equations suggest, and perhaps stranger still in ways the equations have not yet reached. The scientists will go back to their laboratories and their telescopes and their blackboards and their computers. The experiments will continue, the measurements will accumulate, the papers will be written and reviewed and published and contested and revised. The great project of understanding, the longest, most difficult, most important project that human beings have ever undertaken, will go on, as it has always gone on, driven by the specifically human conviction that the world can be understood and that the attempt to understand it is worth making even when, perhaps especially when, the understanding achieved reveals more mystery than it resolves. This conviction is not naive. It has produced everything that science has ever discovered. And everything that science has ever discovered has confirmed that the universe is more extraordinary, more complex, more surprising, and more deeply unknown than the scientists who made each discovery expected. Progress and mystery have always traveled together. The deeper we go, the more there is to find. And the most important experiments have always been the ones whose results nobody predicted, the ones that arrived from the universe like a message from somewhere very far away, written in a language that took years or decades to decipher, pointing toward a reality that nobody had previously imagined. That message is being received right now, in the data from the Muon G2 experiment, in the Hubble tension measurements, in the silence of the dark matter detectors, in the quantum eraser results, in the Wheeler-DeWitt equation's missing time, in the holographic entropy calculations, in the discrepancies between early universe simulations and the galaxies the James Webb Space Telescope is actually finding, in the mathematical infinities that appear wherever anyone tries to build a complete theory of quantum gravity. The messages being received, translated word by word into the language of physics, and the translation so far reads something like this: "You have not yet understood what we are. You have described our surface with remarkable precision, but the surface is not the depth, and the depth is different from anything you have imagined so far. Keep looking, think more carefully, question the things you are most certain of. The answer is not in the place you have been looking. It may not be in any place at all, in the sense you mean when you say place. It may require you to change not just your theory, but the way you think about what a theory is, what reality is, what knowing is, what you are. Keep looking." And so the question that started all of this, the question implied by every anomaly, every paradox, every unanswered measurement, every incompatible theory, was never really about physics. It was always about something older and deeper and more intimate than physics. It was about what it means to exist inside a reality that you did not choose and cannot fully understand, using tools that are themselves made of the mystery they are trying to unravel, asking questions that may or may not have answers, pressing always forward into a darkness that retreats exactly as fast as the light of understanding advances. It was about whether the universe at its deepest level is knowable at all, and the honest answer, the only honest answer that the evidence and the theory and the history of science together support, is we do not know. We do not know if the universe is fully knowable. We do not know if there are truths about its nature that are, in principle, permanently beyond the reach of any observer embedded within it. We do not know what lies beyond the observable horizon, or beneath the Planck scale, or on the other side of the event horizon, or in the inaccessible branches of the quantum multiverse. We do not know what dark matter is, or what dark energy is, or why the cosmological constant has the value it has, or why time has a direction, or why anything exists rather than nothing. We do not know. And that, the sheer, vast, scientifically grounded, experimentally confirmed, theoretically motivated depth of what we do not know, is the most important thing that science has ever discovered, because somewhere in that depth of unknowing is the answer. Not the answer to a specific question, not the solution to a specific anomaly, but the answer that changes everything. The insight that will make the next generation look back at our current understanding the way we look back at the understanding of people who believed the sun revolved around the earth. It is there, in the data that has already been collected, in the equations that have already been written, in the experimental results that have already been published, in the discrepancies that have already been measured, in the questions that have already been asked, in the silence of the detectors and the tension between the measurements and the infinity and the equations, and the missing time, and the invisible matter and the accelerating expansion and the uncollapsed wave function, and the unresolved paradox and the unanswerable question. It is all there, waiting, not for more data, necessarily, not for a more powerful accelerator or a more sensitive detector or a more distant telescope, though all of those will help, waiting for a mind that sees it differently, waiting for the moment when someone looks at what everyone has been looking at and sees, for the first time, what it actually is. That moment has not come, but it is coming. It is always coming. And until it does, this is where we are, inside a universe that works perfectly by the equations we have and that refuses to be fully explained by them. Inside a reality that is as solid and reliable as it has ever been on the surface, and as strange and uncertain and open and unresolved as it has ever been in the depths. Standing at the edge of what is known, looking out into what is not, holding the question without the answer, feeling the specific vertigo of genuine not knowing, not the comfortable not knowing of someone who has not yet looked, but the profound not knowing of someone who has looked as hard as it is possible to look and found, at the very limit of the possible, not an answer, but a deeper and more beautiful question. Reality has not broken in the sense of stopping. It continues exactly as it always has, indifferent to our confusion, following its own inscrutable rules with perfect fidelity, producing its quantum superpositions and its entangled correlations and its emergent space-time and its accelerating expansion and its invisible matter and its inaccessible depths, doing all of this simultaneously and consistently and without any apparent awareness that any of it requires explanation. The breaking is in us, in the frameworks we built, in the certainties we held, in the assumption that the world was, in principle, fully comprehensible by the minds that inhabit it. That assumption has been broken, not by failure, by success, by the success of science taken to its furthest conclusions, where the conclusions themselves begin to dissolve into something that the science cannot yet name. The world is not less real for being stranger than we thought. It is more real, more itself, more independent of our expectations, more fully whatever it actually is, and less whatever we imagined it to be. And you who have followed this all the way to the end, who have sat with the anomalies and the paradoxes and the unanswered questions and the slowly eroding certainties, you are different from who you were at the beginning, not because you know more, though perhaps you do, but because something has shifted in the relationship between your certainty and the world that certainty was attached to. The world feels the same. The coffee is still hot. The ground is still solid. The people you love are still there. And yet the ground beneath the ground, the foundation of the foundation, the deepest level of what all of this is resting on, is something you now know to be genuinely, profoundly, scientifically uncertain. And that uncertainty is not a flaw in your understanding. It is the most accurate thing your understanding has ever contained. It is the truth that all the most precise measurements, all the most rigorous theories, all the most careful experiments have converged upon. At the deepest level, the universe is not yet understood. And the question of what it actually is, what is really there, beneath the surface of appearances and measurements and theories and frameworks, remains, as it has always remained, as it may always remain, completely, devastatingly, magnificently open. What then is reality? You already know the answer is not simple. You already know the answer is not available. But perhaps the most honest and the most important thing that can be said is this: reality is the thing that keeps surprising us. Reality is the thing that refuses to be fully contained by any description of it. Reality is the thing that answers our most careful questions with deeper questions, that responds to our most precise measurements with new anomalies, that takes our most powerful theories and shows us at their edges where they break down and something unknown begins. Reality is the pressure behind the data that does not fit, the silence in the detector that expected a signal, the interference pattern that should not be there, the expansion rate that two instruments cannot agree on, the infinite density at the center of the equations, the wave function that never quite collapses all the way down, the time that disappears from the quantum gravity equations, the information that may or may not survive the death of a black hole. Reality is all of that. And it is also the coffee and the sunlight and the weight of the air and the face of the person you love and the specific quality of this moment, right now, in which you are aware that you exist and aware that you do not know what that means. All of it is real. All of it is the same reality, and none of it, not the familiar surface, not the quantum depths, not the cosmological distances, not the Planck scale foundations, none of it is yet understood well enough to be certain about, which means the question is still open, which means the inquiry continues, which means there is still everything to discover.